Wow, great. Well, yeah, thank you so much for having me. That was probably one of the best introductions I've ever received. That was a lot all at once. That's a lot to live up to. Hopefully, you guys enjoyed the session. But yeah, thank you so much for having me. And I'll go ahead and turn on a screen share here, and we can get started. All right. Let me know if that's coming through, Roberto. Comes through. Got it. All right. Perfect. Great. All right, good deal. Well, welcome everyone. Thanks for spending some of your Sunday with me today. I'm excited to be here and walk through some deep learning for computer vision. This is a field that I've worked in for 5 to 10 years, depending on how you count exactly. And it's a really exciting time to work in computer vision. There's just a lot of really neat stuff happening, and you can really have a big impact in this space, in my opinion, relatively quickly, just because it's changing so fast. So there's just a million cool opportunities. So I hope today that walking through these different sessions I have set up and walking through some deployment stuff, I hope that really helps give you some context for what's going on in computer vision. And we'll walk through some what I consider to be some pretty cool stuff. Hopefully you think so too. But yeah, let's go ahead and get started. So all the material you'll need for today is at the GitHub site that I created for this workshop. So the URL is down here at the bottom of the screen. So it's github.com/Stephen C, as in cat, Welch, and then it's DSGO-DL-workshop-summer-2020. So I'll leave this here for a little bit to allow you to go to that URL. I really do recommend following along. We're here for 2.5 hours, so I think if you're just listening to me for that long, you might get a little bored, and it's always helpful to follow along, even if it's just a little bit. So I'll leave this URL up on the screen for 5 minutes or so for the late joiners. And I'll go ahead and start giving you an overview of what we're going to talk about here today. So I've pointed my browser at that link, which I realize I've just made go away. There it is back. So here I am on the GitHub page. And this is our material for today. So let me scroll down a little bit, and we'll talk about our agenda here. So here's how we'll spend our time today. So it's 1 p.m. Pacific time, and depending on where you are, of course, it's a different time. I'm in Charlotte, North Carolina, so it is 4 p.m. So we'll spend a little bit of time just getting acclimated to everything here and give you some time to get to the GitHub site. And then we'll spend a little bit of time setting up your computing environment. So we're going to use, the easiest option will be Google Colab, and we'll get into that into some details. But if you want to be hardcore and train on your own Linux machine, you can do that as well, and I'll spend a little bit of time showing you how to set that up. And then we'll go back and talk just a little bit about the history of computer vision. I really like bringing in some history here. I think that computer vision's around 70 years old, so not that old, right? There's people that are older than computer vision. And a lot of really smart people have done a lot of cool things in computer vision. And I think, as if you're new to the field, or even if you've worked in the field for 5 or 10 years, it's easy to focus on the new, really shiny stuff. But there's really just a wealth of great research that's happened over those 70 years. So we'll spend a little bit of time talking about history, but we will spend most of our time today on modern deep learning techniques. But the history is just really, really fascinating. And I think it really does inform your practice. It's not just, an interesting, entertaining story. It also, I think, can make you a better deep learning, machine learning practitioner. So the meat of our time today, we're really going to do 4 things. So first, we're going to train an image classifier, which is kind of the one of the simpler things to do. We'll mix it up a little bit and use a different data set than you've probably seen before. And we'll kind of walk through some of the nuance. We're going to use my favorite library to date, which is FastAI. We'll talk about FastAI a little bit and some of the trade-offs that you make when you choose a library like FastAI. And then we'll do bounding box detection, which is another very popular kind of deep learning model. Instead of just using something out of the box, kind of like YOLO or something, we are going to build our own, which should be pretty fun. Hopefully it goes well. Then at this point, I'm going to assume that you're sick of hearing me talk, or you want a little bit of time to catch up, and we'll take a short little break, and I'm going to get some water or something, because I'm sure my voice will be tired. And then we'll pick back up with semantic segmentation at around 2:20 Pacific time. And then we're going to do the really cool part, I think, which is deploying this stuff. The deployment is really critical, and I think in the industry today, you're really seeing a shift and a focus on the deployment tooling, which is exciting. When I started working on neural networks in like 2012 or so, the tooling was just, man, I actually wrote my own library because the tooling was so bad. And today that's not true at all, and there's a lot of great tools. So we're going to be using Docker and Render, which is a cloud platform, to actually deploy a model that we built today. We're going to deploy it as a web app, which is, I think, pretty cool. If for some reason we go really fast and we move quickly, then we'll spend some time at the end talking about a really cool new technology in computer vision called a GAN, a generative adversarial network. And then if we really have extra time, which I don't think we will, but just in case, I've got a few slides kind of reflecting on studying AI in 2020. So that's the agenda for today. Hopefully that all makes sense. And yeah, let's go ahead and dive into it here. So I still have this link up, and I do encourage you to go to this site here. And the first thing is just what are we going to do today? And hopefully this is clear, but we're going to train and deploy some deep learning computer vision models and hopefully have some fun along the way. So let's go ahead and get into our first area here, and that's going to be setting up your computing environment. So I've given you three options here, and they're kind of in order of difficulty. And this, I think, reflects not just on today's workshop, but just in general. You know, if you're a deep learning practitioner, or you're getting into it, or you've been in it for a while, then it's worth thinking about the environment you use, the compute that you use to work on these problems, because it will make a difference. So in my opinion, you know, the easiest thing to use is Google Colab. I very rarely use this kind of at work in production. Not that you couldn't. It's just there's not quite enough features. But as far as like fast experimentation, it's hard to beat. And let me show you what I mean. So if I go back up here, so our first notebook is going to be this image classification notebook, right? So I'm going to open this in a new tab. So I'm going to click here, and we'll lose our link, but it's up here if you need it. I'm going to open this in a new tab. So here we go. And you know, if you haven't seen Google Colab before, I'm guessing a lot of folks have, but if you haven't, you know, we're already in a live coding environment, which we'll start using in a minute, but we can start running code right away. So it literally is a one-click computing environment, that's just crazy. That's such a nice tool to have. That's an awesome thing to have. So I mean, let's look at the setup for that. There is one thing you have to do, so let's walk through that real quick. So here's my Google Colab setup. It's section 2.1 if you're looking at the README. And you do need a Google account. So if you don't have a Google account, you'll have to make one. That shouldn't take too long. So it's not one click for everyone. I should say you do have to have a Google account. So I'll be talking through setup for 5 or 10 minutes. So if you don't have one, now's a good chance to make one. Let's see here. Let's go through the only configuration change you have to make. Yeah, here it is. So the only configuration change you're required to make is changing your runtime. So all we're going to do here, so I would recommend go ahead, even if you're not going to use Colab, it's nice to have as an option. So I'd recommend go ahead and open this up. And when you're in Colab, you can go to Runtime, and you can go to Change Runtime Type. And I'll just show you that again a little more slowly. So Runtime up here, Change Runtime Type. And this is just as incredible about Google Colab. So you can just turn on a GPU. Now, they aren't always available, but just having this as an option is amazing. So go ahead and change this to GPU. That's a graphical processing unit. This is the accelerated compute power we'll need to train these models today. And click Save. And that will change you to a GPU backend. Now, well, actually, yeah, I was going to have you go ahead and run a cell, but let's wait until we get through a little bit more setup. So that's literally all the setup you have to do. And actually, while we're here, just real quick, I'll just have you run a couple cells. So let me make sure everyone knows how I got here. So to get here, I right-clicked on Open in Colab. I opened it in a new tab. And here, I went to Runtime, and I changed Runtime Type to GPU. So that's where I am. And if you are here, I might just have you go ahead and run 2 cells just to start your data download, actually 3 cells, just to have that going in the background. We're going to be using some data from a server that I host, and I don't want to stall. If we all hit it at the same time, it might be a problem. So the more we spread this out, the better. But go ahead and try. So if you're in the notebook, click on this first cell right here. And to run the cell, you can press this play button, or you can press Shift-Enter. If you're, oh, cool, and it'll give you a little warning. This code was not authored by Google. It was authored by me. So I promise you I didn't put any viruses in it. So you should be fine to run it. So run this cell, and please go ahead and run this cell. So these 3 cells. What that's going to do, and I'll come back to this one more time, but it's going to go ahead and start a download. It's going to start downloading the data set for you. And like I said, it's just a nice thing to have going in the background, especially if your internet's a little bit slower. Starting this download now is probably a good idea. So I'll go back to our README here. So yeah, back to setting up the computing environment. So again, Colab is just a really easy way to get going here. And there are some cons. The GPUs aren't always available. There's limited session times. You can't have a notebook open forever. There's limited RAM. You can pay more for that stuff, but just keep these things in mind as you're thinking about what makes sense for you. The next option is your own Linux GPU machine. So if you are, I would say, if this is something that you're doing regularly, if you're spending a lot of time on it, if you're doing it for work, it's going to make sense to buy your own machine sooner or later. VMs are great, but it's hard to beat being plugged into your own machine. So if you happen to have one, you're welcome to use it for this workshop. It does take some time to configure, and I'll just walk through a few steps with you. I don't want to waste everyone's time on GPU configuration, but we'll just spend a couple minutes on it here. And then I won't spend any time on the third option, but this might be a pattern that some of you are comfortable with, and if you are, then feel free to use a virtual machine. So a virtual machine, if you don't know, you can rent a server in the cloud from Azure or from AWS or from Google or whoever. And you can SSH into that machine basically and use it just like it's your desktop, which is pretty cool. They can be difficult to configure sometimes. You only get a terminal-based interface, and they do cost a little bit. If you run this for a day, it's $24, so it will add up. But that's also an option. So I won't walk through this one in detail, but I'll walk you through a little detail on your own machine. And even if you don't have a Linux GPU machine that you're using right now, if you have a Mac or a Windows computer, you may want to go ahead and follow along because we're going to be cloning the repo, which is kind of a nice thing to have anyway. So let's walk through that a little bit. So if you want to use your own machine, or at least try on your own machine, or have some of this on your own machine, the first thing I recommend is installing Anaconda Python. So Anaconda Python is a distribution of Python that has a nice package manager that comes with it. There's other ways to do all this stuff, but Python makes things pretty straightforward. So if you don't have this installed, it's a clickable download thing. You just click your operating system here, and the setup is pretty straightforward. So for me, if I was on Linux, I would use this one, for example. Excuse me. So that's the first step here. After you get that done, what you want to do is you want to go into a terminal. What I've actually done here is I'm at my desk right now, and I'm on my laptop, my MacBook, but I have a GPU machine over here. Maybe I can actually show you real quick. Let's see. I don't want to mess with my cables. There's a GPU machine right there. I think you can see it. Anyway, I am going to SSH into that machine. Just to have, I'm going to use Colab mostly along with you guys, but I'll just have this as a backup just in case. So here I'm remote accessed into my GPU desktop machine that's next to me. Here I am. And I'll actually walk through some of these commands. So if you are on a virtual machine or you just want to clone the code, which is not a bad idea, this is the command you would run. So git clone with a link to the repo. So I'll go ahead and do that here. Hopefully that works pretty well. My internet is pretty snappy today. It hasn't given me any problems yet. Fingers crossed. All right, cool. So I cloned the repo. And now I should have a repo called that, which is like DataScienceGO DL workshop. Yeah, cool. Oops, I typed ls. So I'm gonna navigate into that directory. So DSGO, cool. So CD is change directory. So here I am. This is our code for today in our notebooks. Now you will need some dependencies. This is where Google Colab is amazing because it does all this for you, right? What I recommend is if you're using Conda, to create a new virtual environment. So a new Conda environment will kind of separate your different computing environments on your computer, which is kind of a nice thing to have. So what I'm doing with this line of code, Conda create, so -n is for new. I'm creating a virtual environment called DSGO-CV, and I'm saying, okay, I would like to use Python 3.7 in this environment. So I'll go ahead and run that. I already have a virtual environment called this, so I'm going to remove the existing one. You shouldn't have one called this, highly unlikely. And I'm going to proceed here. So I'm setting up my environment. That was pretty easy. And this is telling me, okay, if you want to use your virtual environment, you can do conda activate DSGO-CV. So I'll do that real quick because I'm going to activate my virtual environment. And all the commands are here on the README. So if you're falling behind or anything, just don't worry, it's all in the README there. And again, you don't have to have this set up on your computer to code along, but it can be a nice thing. And the last thing I'll do is I'm going to install the requirements. So there's a number of packages. I can go ahead and show you that real quick. So here I have the repo open in a text editor. And these are all of the requirements that we need, all the different packages. Some of these packages are going to be used for deployment at the end. But you'll notice things like, let's see what's interesting. So Jupyter, that's a Jupyter notebook for us. Matplotlib, so we can plot stuff. So those are all the packages we need. So to install those, I type pip install-r requirements, like that, .txt. And this should install all my requirements. Okay, I think we're almost there. It's taking a minute. And after you do that, we're really almost done. All you'll do then is launch a Jupyter notebook. Cool. All right, so those are still running. I'll let those continue to run. But if you want to set up your own environment, that's how you do it basically. If you are on a Mac or if you're on Windows, there might be some idiosyncrasies with how you install your environment, which is why I really only officially recommend this if you're on Linux. You're welcome to try this, and the cloning should be fine on any operating system, but there can be weirdness in different operating systems, and I haven't tested all this code against different operating systems. I had more time. So that's the setup. Again, Colab is going to be easiest. If you want to clone the repo, feel free to. It's nice to have it locally on your machine as well. But that's really section 2. So that's our setup. I'm going to take a little sip of water here, and we can look at our next section here. But hopefully at this point, you've either just opened up a Colab notebook, and maybe you've downloaded some data already. And we'll do this again. Oh no, my download's getting slow. That's not a good sign. I bet my little server is getting hit. I should probably put a Dropbox link as well. So this is my little server. So we'll see how it does. And if it has any issues, I will use a backup version I have, and we'll talk through it while you're getting the download. Okay, so now that we have that set up, our next section here is we're going to talk just a little bit about the history, kind of how we got here in computer vision. Now, what I do want to make sure is that while I'm doing that, you guys all have a chance to download the data that you're going to need. I want to make sure that we don't waste our time trying to download data later. So let's do this. So let's spend a little bit more time in the notebook so you each have a chance to download data. And then I'll come back, and as I'm talking about the next section, you can all hopefully be downloading data. So if you're running locally and you've installed all these packages, you can launch a Jupyter server by typing Jupyter notebook, and that should be all you have to type. For me, I am SSH'd into a machine on my local network, so I need to figure out, let's see here, my IP address. I think I have it written down. Oh, there it is. Cool. Great. Okay. So because I'm SSH'd into a computer on my network, I'm going to type a slightly different command. So for everyone running at home, you can just type Jupyter notebook. I'm going to type --IP and my IP address, and that should be everything I need. Cool. All right. I'm just going to have this running as an option. Copy. Cool. All right. So this should show up. Oh, maybe not. This is the beauty of live coding. Let's see here. Cool. Okay. Much better. Great. All right. And I'm actually going to start this download as well on this machine, just in case. And I think I already have this downloaded, but I might not have cached it because I just recloned the. Yeah, there we go. Cool. All right. So I'm starting the download there. I just want to make sure that I have a data set I can show you guys, because this one is hanging right now. Okay. Cool. All right, so that's that. I'm going to set that aside for now. And again, for most folks, I recommend using Google Colab. And just to give it one last review before I really hop into the meat here, so if you're new or you just joined, please go to this URL. You can also see it in my address bar up here. So it's Stephen C. Welch /DSGO-DL-workshop-summer-2020. And when you arrive there, if you scroll down to here, all you have to do to code along is right-click here and go Open Link in New Tab. And this will put you in a notebook where you can code along with me. All right, and I'm going to actually, and when you get here, go to Runtime, go to Change Runtime Type, and change it to GPU. Okay, and I'm going to actually restart my runtime because my download seems to have stalled, which is annoying. If you're able to successfully download, maybe just let us know in the chat. I want to make sure that at least a decent portion of you guys are able to get the data. So all I'm doing here, if you haven't used Colab, is I've scrolled down to the first few code blocks, and I've ran this one, I've run this one, and I've run this one. So please do those 3 things, just so you can have your data downloading in the background as we talk about the next section. I'm kind of curious now to see if mine actually finishes. Oh, good. I think it's going to finish. Okay, great. Excellent. Okay, good. All right, so yeah, please go ahead and do that. And I will give us some background now before we really hop into the meat of this notebook. Okay, cool. All right, so we have made it through setting up your environment, and now it's story time. And we are 7 minutes behind schedule. All right, hopefully I'm going at a decent pace here. All right, cool. So let's talk a little bit about computer vision. So computer vision is really just there's so many cool stories. It's a really cool discipline. I really encourage you to spend some time in it. If you already have, great. You probably already know that. But it's obviously it's a way to make money and it's a cool job to work in, right? But it's also just, I don't know, I would probably study it anyway. I would think it's just a really cool topic with cool histories and cool problems. So let's go back 50 years or so to the summer of 1966, which I guess is, 54 years now. So back then at MIT, Marvin Minsky, he was a professor there at the time. He's a kind of a really well-known character in AI. Some people call him the father of AI. Him and Seymour Papert, who's also a really interesting character. He, what is that programming language he invented? I forgot. It'll come to me in a minute. But anyway, they started to work on computer vision. So there was an AI lab at MIT, and they decided to work on computer vision. They had a video camera hooked up to a computer. It's very rudimentary, but they could get pixel values. So they hired Gerald Sussman, who was an undergraduate at the time, and they set up a summer project. And let's look at their summer project. So this is the abstract that Seymour Papert prepared for their summer project in 1966. So he said, the Summer Vision Project is an attempt to use our workers effectively in the construction of a significant part of the visual system. So what they mean literally is a significant part of the human visual system. So they're saying, let's go out there and make a computer act like a human visual system, which maybe that sounds easy, maybe it sounds hard, I don't know. Depends on your background probably. But to me, that sounds very audacious. Which I think is, there's all kinds of cool stories in the history of AI about if you zoom out and forget how computers work, it might seem easy because you can see, I can see, right? We kind of take it for granted, right? It turns out seeing is really hard. So they went on to say, the particular task was chosen because it can be segmented into subproblems, and they kind of talked about how they're going to break it down, and it's going to be a real a system complex enough to be a real landmark in the development of pattern recognition. So that was the goal. And being good project managers, they broke it apart. So here's another excerpt from the original abstract for the Summer Vision project at MIT. So the sub-goal for July was the analysis of scenes consisting of non-overlapping objects from the following set. So balls, bricks, and cylinders. And the goal was to figure out, what was in the image, right? They wanted to do analysis on the image and figure out, does it contain a ball, a brick, or a cylinder? The extension for August, so they're assuming they can get this done in 1 month, right? This is a 1 month goal, okay? The extension for August is that it'll be really like a noisy, cluttered background, and then other kinds of cylinders or other kinds of balls, for example, like a battery, and then extend to new classes. So these are, really some of the most brilliant AI researchers in the world, and they thought in 1 month they could solve this, right? They could tell bricks, balls, and cylinders apart. So let's get into the details here a little bit. So yeah, before I give any spoilers about what kind of happened, let's talk about computer vision and why it's a little bit hard. And actually maybe I'll tell you a little bit more about that project. So it turns out it was a lot tougher than they thought, and really to really solve these problems that they're talking about, ball, brick, and cylinder on a cluttered background, it was kind of solved maybe 20 or 30 years later, but I would say it wasn't really solved until like 10 years ago. So it really took like 40 or 50 years to solve this, and it's funny to look back, right? So this seemed like a month-long project, and it's not because these people were dumb; they're really brilliant, right? It's just that at the time, AI was relatively new, and it seemed like it was going to be pretty easy. There's a really good word for this, or a good phrase that captures this. It's Moravec's paradox. Named for Hans Moravec, an AI researcher, and he says basically that the hard problems are easy and the easy problems are hard. Vision seems really easy, right? Because we do it all the time. It's easy. It feels easy, but it's really hard to get a computer to do vision well. There's another great quote from an early computer vision book. This is by Peter Hart and Richard Duda. Here's a link to the book if you're interested. You can buy it for $12. It is old, it's from the 70s, but it really captures a lot of the challenges really, really well. Some of these old books are just great. But there's a great quote from it. They say, paradoxically, we are all experts at perception, but none of us knows much about it, which I think really captures this well, right? We know how to see, but we don't know how we're doing it, right? You can't sit down and write down instructions that describe how you're able to see me right now, right? So the cool thing, and I hope this makes you excited to do this workshop. I think it's exciting. Is today, literally before we're done, we're going to do exactly what Minsky and Pepera set out to do. We're gonna solve this exact problem. Now that is assuming my server works and you can get data and all that good stuff, and technology gods smile on us. But this is very achievable today. But it really wasn't 10 years ago. You could maybe do it 10 years ago under some constraints, but deep learning has really changed what's possible. So I'm not going to bore you with a ton of history. I could talk about history for the whole time if easily, but I want to get into some applied modern stuff. But there's just one more historical thing that I really want to point out. And I think it's worth knowing because, again, it will make you a better practitioner, in my opinion. And that's the idea of the trade-off between an analytical and an empirical technique. So analytical versus empirical. These are just great concepts to know as you're working on algorithms. They come up for me all the time. I think they're worth spending some time on. So here's an image from a class I teach. So I teach a computer vision class at the University of North Carolina at Charlotte. And this is part of an analytical pipeline for recognizing a brick. And when I say analytical, what I really mean is that this is like based on knowledge. So a human sat down and said, okay, let me think here. What kind of algorithm, what kind of math can I do to the pixel values in this image to figure out what's in the image, right? Analytical pipeline means like it comes from reason, right? So we sit down and when we make this pipeline, we design it, we engineer it. It's human engineered. So the way this pipeline works, I'll just give you a quick overview of it. If you're interested, I have some lectures on this. But this is a pipeline called the Hough transform. So we take this image of a brick, and this is actually a video of a brick, but same idea. We do something called the Sobel-Feldman operator, which is a piece of math that helps you find the edges of an object. You take those and you do this other piece of math called the Hough transform. It's really beautiful math. It's really cool. So you transform all these points into this space of essentially it corresponds to the two different locations are a parameterized version of a line. So it's almost like, it would take a little while to explain, but like the line equation y equals mx plus b, you kind of use that equation to map to a different space. It's really fascinating. But anyway, when you map these points to this space, the points become curves, and the intersections of the curves, where there's lots of curves in one little point, correspond actually to lines in Hough space. So these lines are mapped, I should say they're points in Hough space, but they correspond to lines in our image space. So we compute these intersections, we find this point, and we map it back here, and then we can detect lines. So this is an analytical pipeline because all the steps are figured out by humans, right? We sit down and we come up with some math. We invent some math to solve the problem. So these pipelines can be very successful, and they've solved a lot of computer vision problems. Right now, however, the best algorithms out there are empirical. So again, analytical versus empirical. Deep learning is a very, very empirical technique. And when I say empirical, I mean it's data-driven. So instead of sitting down and developing this pipeline by hand, we're going to actually just have a labeled data set, and we're going to make this algorithm, but we're not going to design the algorithm. We'll design the structure of the algorithm, but the algorithm itself will learn to do the task that we want it to, which is pretty crazy. So today, most modern I shouldn't say most, but a lot of the cutting edge techniques today are empirical. They're data-driven. But I would say, especially if you're new in the field, just maybe understand that this is what's hot right now, but it's not always going to be the case. So these things are cyclical. I guarantee you, in 20 years, there's going to be something else that's popular, and that's fine. That's how things kind of progress and move. There's a cycle to it. So we're going to spend our time today in computer vision on deep learning, which really is really the state of the art right now. But don't forget about the other stuff, is all I'm saying. And if you see a new computer vision problem, don't immediately hop to deep learning, because deep learning comes with some baggage. There's, we'll get into it today. There's some tough parts. So it's not the only tool out there, and there's a whole body of analytical computer vision out there. If you're curious, the OpenCV library is a great place to start. It's got Python binding. It's really easy to use. Documentation's great. It can be a little clunky sometimes, but there's lots of great tools out there beyond deep learning. So just be aware of those before we spend the next 2 hours on deep learning. Okay, so that's my diatribe, and I'll get into what we're doing today. So here's our data set for today. So remember that I said today our job is to build, train, and deploy a model that solves the problem that Minsky and Pépère and Sussman set out to solve back at MIT in 1966, which was to differentiate balls, bricks, and cylinders in cluttered backgrounds. So this is part of the course I teach again. We have this little data set that I collected. I call it the BBC 1K data set, so BBC for brick, ball, cylinder. And thanks to some really awesome TAs that I work with, we have it very well labeled, which you'll see in a minute. So it's got about 1,000 images, around 300 images of bricks, 300 images of balls, 300 images of cylinders, across all different kinds of backgrounds. So that's going to be our data set for today. Hopefully, in the background, you're downloading it right now. Hopefully, this command is working. If not, oh yeah, one more thing actually, real quick. If it's not working, you can actually download it. Do I have a link to it? There should be a link here. You can download it manually. However, yeah, it's here. However, that won't get it into Collab easily. You can get it into Collab through Google Drive, but but there are a couple other options if you have any download problems. Okay, so this is our data set for today. And just to show you the labels a little bit, so again, myself and my TAs for my course have labeled this data set. And we've done what's called a segmentation label, which is we try to the best of our ability, the best of our ability given our time constraints, to draw nice tight regions around each of the objects. So roughly we have, at the pixel level, we have the region that corresponds to that object labeled. So it's a pretty time-consuming process. You sit down and you draw these points, a polygon around the object. There's some really good tools out there that are pretty easy to use. We use LabelMe for this data set. But we draw this region, and then I'm actually computing the bounding box. We're going to do some stuff with bounding boxes, and I'm just computing these bounding boxes by taking the outside of this region, basically the extrema points. But this is our data set for today, and if we're successful, we'll be able to do three things. We'll be able to classify these images, we'll be able to compute bounding boxes for these images, and we'll be able to segment these images. So that's really our goal for today, and to deploy that code. Saying that all out loud now makes me think I should go a little faster because we've got a lot to do. Okay, so if you're interested in any of that, here's my course at UNCC. Feel free to check it out. Also, if you want to contribute to it, feel free to. It's all on GitHub. It's all public. There's lots of room for improvement. I think we've done some cool stuff. I've taught it for 2 years, but there's always room to make it better. So I also have a YouTube series called Learning to See that talks through some of that history as well. Feel free to check that out. That's like 4 years old now. It's pretty crazy, but feel free to check that out. And then finally, oh yeah, if you want to read some more about the history of AI, this is just a great book. The Tumultuous History of the Search for Artificial Intelligence, written by an MIT researcher. Super, super good. I think it's actually out of print, which is really surprising, but highly recommended. So if you want to learn any more about that kind of thread that I just talked about, there's some resources where you can do that. Okay, so now we're on to section 4. So let me go back up to the top here. Okay, so section 4, I was trying to start at, wow, I'm 10 minutes behind now. I keep sliding. Okay, all right, so it's 1:35, and we're going to hop into writing some real code. So if you haven't already, please open up this notebook, either in Collab or on your local machine if you've cloned the repo. And I'm going to go ahead and open up in Google Colab here. And here we are in Google Collaboratory, and I'm going to make this full screen just so we can just really look at our code here. And here's the top. And yeah, I'll talk a little bit more, and then we'll really write some code. If you're in here and you haven't downloaded the data, please scroll down and run these 3 cells, this one, and this one, so you can start getting your data downloaded. Now, let me talk a little bit about the library that we're going to use. So we're going to use a library called FastAI. And it's maybe a little different than some of the libraries you may have used. I think the most popular library is probably, well, I think PyTorch might have just patched TensorFlow, maybe, I'm not sure. But they're both very popular. So there's also Keras, which is kind of a wrapper on PyTorch, or sorry, on TensorFlow. I think it supports other backends too, though. So FastAI is, the metaphor I use basically is FastAI is to PyTorch as Keras is to TensorFlow, roughly. So it's a high-level wrapper for PyTorch. It's developed by Jeremy Howard, Rachel, I forget what is her last name. Let me go back here. Cool, let me go back to, there we go, cool, great. Okay, excellent. So yeah, Jeremy Howard, Rachel Thomas, and Sylvan Guger. So they've written this library, and there's other contributors as well. But Jeremy Howard, if you don't know, he is a co-founder of Kaggle. So he, and also a top Kaggle competitor. I think he was #2 on the Kaggle leaderboards for a while. But he's written this library that wraps PyTorch. And there's some things not to like about FastAI, and you'll probably bump into that. It can be a little hard to debug. It's a little bit dense. But really, in my opinion, in 2020, it is the fastest way to train models. And you can always start with FastAI and switch to other things. But if I'm doing quick experiments, I pretty much always start in FastAI. It's just a very easy to use library, and something they've done that's a little bit different than Keras, I would say, is Keras is probably more of a tool in that it's a little less opinionated. So Keras is like a platform. It's great. It's a really nice library, right? FastAI encodes a bunch of opinions, basically. So you'll find Jeremy Howard and the author's opinions all around with how the syntax works and how things feel. And that's really on purpose. So they've tried to encode some best practices. I find that helpful, but some people are going to find that annoying. So bear with me here. I think even if you want to switch to Keras after today, that's fine. I think you'll still learn some stuff. But that's FastAI in a nutshell, and they have gotten some incredible results in natural language processing. They trained ImageNet in 18 minutes, which is just this crazy benchmark thing they hit. I put a link to it there. Let me get back. Okay, cool. I keep clicking on my own links. So that's a little bit about FastAI. It's the library that we're going to use today. And let's go ahead and hop into it here. So again, if you're new, please run these 3 cells. And what I think I'm going to do here, I'll try it, and if it's too slow, I'll change. But what I'd like to do for a minute is just code from scratch for a minute here. Now, I think because of the way Colab works, I'm going to have to re-download the data, but that's okay. So sometimes at the beginning, it can be helpful to do a little coding from scratch. And let me close a couple of these windows. I've got too many windows open now. Okay, cool. So I went File, New Notebook. You don't have to do this. You can follow in this main notebook. But I'm going to be coding just a little bit of this from scratch because I think that's helpful. So let me rename this notebook. So I'm going to call this Image Classification from Scratch. Cool. All right. And I'm going to copy over a couple things. So I'm going to install wget, which is this is the tool we need to download my dataset. I'm going to copy this cell over as well. This includes just a couple simple methods to download the data. And I'm going to copy over this cell, and then probably one more cell. And again, you can stay in this notebook if you want. I'm just going to create an empty one just so there's not too much distraction, and it's clear kind of what I'm doing. And then we'll see how that goes. We might switch back, but all right, cool. So I'm going to try to download this again. We'll see how it goes. Okay, cool. And I'm going to bring over my imports. All right, great. Okay, cool. Let me get a few blank cells. Great. All right. So while my data is downloading, let's talk about our imports for a second. So I'm going to import just a few things. So PyLab inline, this imports a library called matplotlib for visualization, and it imports a numerical computing library called NumPy. And it's just a quick shortcut to import those things. Here I'm importing the FastAI Vision library. Here I'm importing this pathlib library from standard libpython. This is a really great pathing library that makes life easy. And then finally I'm importing Pandas, which is a really great tabular dataset library. Okay, so I have my dependencies. Now so I'm going to copy over, I guess, one more thing. Although I could probably just do this. Let's see, ls. Oh yeah, cool. So if I run ls, this actually is a shell command. But what this shows like what is the data that's actually sitting on this little server that Google Colab has set up. And I think I can see the same thing if I go here. So if I click on this little folder, yeah, we have data and sample data. Sample data, I think, comes from Google. Yeah, this is their data. They have MNIST and stuff. Data is what we just downloaded, if this worked correctly. Data is what we just downloaded from my server. So inside of there is a folder called BBC Train, and I'm actually going to close this. This is nice to have this graphical view, but we can do all this without using that view if we don't have to. So our data is in data. So I'm going to do something like this. I'm going to say DataPath equals path of data. So this is creating a path to my data, and I'm going to sneak one little look at this real quick. So BBC Train, and we could get to this other ways, but it's in a folder called BBC Train. So this is a pathlib object. Let me make this a little bit bigger. Okay, hopefully everyone can see that okay. So I've made this path to my data, and now I can see what's in there by doing datapath.ls, I believe. Yep, cool. Okay, so this is what's in that data folder. So, and I'm just marching in, and just for a little context here. So, when you're going to train a deep learning model, you need to have some data, right? You need to know where it is. So all I'm doing here is kind of saying, okay, what data did I get from the server? Where is it? What's it look like? What's the format? So we're just kind of walking through and doing a little bit of exploration here before we train our classifier. Okay. So I see that there is a folder called masks. There's this DS store thing, which shouldn't be in there. That's a stupid folder from my MacBook that should not have gotten in there. Let's see here. So there's classification labels. So there's a CSV file. That's interesting. There's a folder called images, and there's a JSON called bboxes. Okay, for bounding boxes. Cool. So what I'm going to do now is I'm going to look at these labels. Let me have a quick look at these labels. So I'm going to use Pandas. So I'm going to load a data frame. I'm going to do pd.from. I think it's from CSV, I think. Why don't I have tab complete? That's weird. Is that not? I don't use Colab a lot. Do I not get tab complete? Oh, I don't know. No, I imported that right. Interesting. If I do pd dot, oh yeah, there's what I want. I'm not sure why I didn't do it like that. Okay, so pd.from. Oh, interesting. All right. Well, let's hop back here. Okay. So yeah, here's what I want to do. It's read CSV. I think I was saying from CSV. There you go. So PD, do I get, oh there, all right, there's the, I was just typing the wrong thing. Okay, so what I want to do, I want to open this CSV file just to see what's inside it. So let me hop back here. So I'm going to do DataFrame, and actually, did I call that labels? Yeah, I'm going to call it labels. So I'm going to say labels equals pandas.read_CSV. And now I'm going to type in the path to those labels. Which are here. So I can actually just type in this. Oh, actually, now I'm going to use the pathlib library. So I'm going to do DataPath /, and the name of the labels is classificationlabels.csv. So I'm going to copy that / boom. Okay, cool. So this should load that CSV file and put it in one of these Pandas DataFrame objects for us. So I'm going to type Shift-Enter to run that. And let's see what we got here. So I'm going to type labels again and press Shift-Enter to have them print out for us. And a nice trick in Pandas, if you just want to see the first few rows just to get a feel for what's going on, you can type head like that, and that will just show you kind of the beginning. And if you want to see more or less, you can actually type the number of things that you want. So if I want 11 things, I can do head of 11, which is kind of cool. I'll go back to just regular head, which is 5 things. So here are our classification labels. So we've put these in a nice CSV, so we have our file names, we have our label, and then I've also done label indices. This can make life easy in some cases. So the label index, so ball is 2, 1 is brick. If we show some more examples, we might see that cylinder should be number 3, I'm guessing. Yep, there it is. So that's how our labels come. Labels come in all different shapes and sizes, so I would say just it's worth having a few tools in your toolbox to be able to look at labels and load labels. And Pandas is a nice tool to have, especially if your labels come in an Excel file or CSV, any of these tabular data formats that you see all around the world. Okay, so we've looked at our labels. Now, let's start by next, excuse me, let's start by actually trying to make a data loader in FastAI that we can use to load our data. So we have our labels in this Pandas data frame. That's great. And actually, just for fun, let's do one more thing. I think we can just do length of df just to see how many labels we have. Oh, I cannot. Oh, I didn't call it df. I called it labels. So length of labels. Cool. Okay. Yeah. So there's 942 labels in this data set. So it's called the BBC 1000 data set, and I think it's 1,000 if you include the training data or testing data. So I didn't lie, but this is just the training data set. All right. Cool. All right, so yeah, we're going to really hop into some FastAI stuff. And another thing that I like, excuse me, another thing that I like about FastAI is that it includes a bunch of really nice data loaders. So we're going to use a data loader called Image Data Bunch. So this data loader called Image Data Bunch. If you're in the notebook or if you're in Colab, you should be able to type a question mark and press Shift-Enter, and it should give you an arg string. This arg string is not very helpful, and this is a great example of where FastAI can be challenging. FastAI 2 is in development now, and I believe it has Swift compatibility, which is pretty cool. Swift is this new programming language that has some very promising early results in machine learning. But that's not great documentation, and there is okay documentation out there. You can go to the FastAI site. What I'm going to do for now, though, is I happen to know that there's this from df method in image data bunch, and what that does is it's a class method that creates an image data bunch from a data frame. And now you can see we're kind of starting to get to some helpful doc strings, right? So if you're in Collab, you'll see this pop up. This is the arguments for image data bunch. And if you are in a Jupyter notebook being served locally, you can press Shift-Tab inside of these parentheses, and you should get the same thing. So these are the arguments. So the first thing is it's asking for a path, and again, it's not a lot of context here, and there's good examples online, but I kind of wanted to walk through just playing with the library a little bit just to kind of hack our way through here, because we do have time, and it's helpful, I think, not to just rush through a pre-built notebook, but to actually build one ourselves. And hopefully you are coding along here. And just for context, all we've done is we've downloaded the data set using the code that I shared, we've imported our libraries, we've set up a data path, we've looked at it, we've imported our labels, and now we are going to set up this image data bunch in FastAI. So the first thing we need is a path. This is a path to our data. I think we may be able to do DataPath, but it might actually need to be the path to the images themselves, which is going to be DataPath /images. Let me show you really fast. So DataPath is just the path to all of our training information, but our images are in an images folder. I'm going to guess, I could be wrong, I'll look at my code in a second, but it's worth a little trial and error here. So I'm going to guess we have to do that. So this is actually the data path to our images, I believe. And just for fun, let me see if anything's in there. So if I put this in parentheses and type ls on the end, yeah, look at that, cool. So that ls command lists what's in the directory, and there's a bunch of images, so that's cool. And I just want to see the first 5, so I'll do, oops, that's of 5, okay. There we go. I would like to see the first 5, so I can do :5. There we go. Cool. Okay. So I'm guessing that's the right path. FastAI will complain if it's not, and we'll deal with that when we get to it. The next thing it asks for is a data frame. So a Pandas data frame is what it asks for, and we happen to have one of those. It's called labels. So let's try to use it here. So let's pass in labels, and I'm going to use my keyword arguments here just to make things really clear. Oh, can I see my doc string again, please? No? Forgive me, I'm not fully used to Collab. I usually use local notebooks, but how do I get my doc string back? Let me try this. That's a little annoying. Here's my hacky solution. There we go. All right, I got it back like that. All right. So yeah, so it asks for a data frame. The variable name is df. I'm going to say df equals labels. So I'm passing in this data frame of labels. And let's see, what else is it asking for? A label delimiter. Interesting. So I might have to pass in a comma there. This is a CSV file after all. We'll see though. I'm going to ignore that for a second. The default value is none. We'll see what happens. So valid PCT. So maybe take a guess and see what you think that is. That is actually the percentage of our overall data to use as a validation set. This is kind of where we start getting into the idea that FastAI is going to really encode best practices for you. They almost force you to have a validation set. And if you don't know, a validation set is a way to make sure that this really bad thing doesn't happen. So the really bad thing is called overfitting. Overfitting is the devil. So it's okay early on to overfit when you're training, but in production and deployment, overfitting can really trick you, because what happens is you think you have this great model, but in fact you don't, because you've overfit to the training data. So these deep learning models are super powerful, and they're so powerful that they can kind of memorize the training set. Not exactly memorize, but kind of memorize. And the way to guard against that is to set aside part of your data, called a validation set, and as you're training, to measure performance on that validation set, but not train on it, right? So it's kind of like a held out set. You're holding it out and just using it to see how you're doing. So we'll do that as we train here, and that will make sure that we're not overfitting. So I'm going to use the default, but I'm going to type it in anyway. So valid PCT equals 0.2, and I got my little screen here back. I'm not sure why. All right. So FN, I'm guessing that FN stands for file name column. And again, there are examples of this out there, but I just wanted to walk you through using the FastAI library like this. So the file names in our columns are stored in a column, or the file names in our label CSV file are stored in a column called file name. So FN column, I believe, is just going to be file name. So I'll put that there. And let's see, what else do we need here? Label column. We need a label column. So the name of the label column is label. Pretty exciting. All right. Label column equals label. Okay. And I lost my really nice, let's see if I can get it back. Cool. Okay. So label column is just label. And am I missing anything else? That might be it. I'm guessing there's some more stuff we're going to want to add. And I'm going to go back and look at my notebook in a second. But I just want to see if this runs. Let's see if FastAI is happy with me or not. We'll see. So I'm going to run this, and we'll see if it complains. Oh, hey, look at that. It didn't complain. All right, so that's lucky. Okay, great. So let's look at this output. So it has created something called an image data bunch, right? And it's separated this into a training set and a testing set, or a validation set, excuse me. And because we chose 20% as our validation percentage, it randomly chose 188, which is 20% of our data, examples to use for validation. These are the images, the image dimensions. These are the categories, brick, ball, ball, brick. And this is the path to the data. So there we go. So cool. So we made an image data bunch. Now, if I remember in my original notebook, oh, runtime disconnected. That's fun. Okay. I think I added a few more things. So yeah, here's a few more things that I added. So I'm going to go ahead and bring this over. And if you're just working through this notebook, that's totally fine. You don't have to make one from scratch like I am, but I think it's just helpful when you're introducing these concepts to kind of see the mistakes I make, because it's I think that just shows you kind of my thought process here. I tend to enjoy the lectures where people just show you the whole process. So this is the whole process. There's two more things. There's two more things that I did not have here that I would like to add now. And these are not mandatory, but they make life easier, and they help our model train. So let's get into them here. So everything matches. I got lucky, except there's 3 new things. So let's walk through these briefly. 4 new things, actually. So DSTFMS. So these are dataset transforms. So this get transforms thing, this is a method in FastAI. I'll just run it here to show you what happens. This is kind of, again, what I mean by encoding some best practices. So if I just type get transforms, I get a set of basically PyTorch transformations that will randomly augment my data. Data augmentation is a great way to train deep learning models. Basically, it applies random crops and flips and warps and rotations. And these things help your model generalize by making it appear that we have more data, basically. So I'm passing in those transforms to do data augmentation. Size, here I'm resizing our data. So in general, you need your data to all be the same size. This data set, I can't remember. It might be, but it might not be. So it's a good practice to resize. And in general, you want to start with smaller images. 256 is actually kind of big, but it's fine for here. You could go down to 128 or 64. And then finally, BS is for batch size. So this is how many images I'm using at a time to train the model. If you run out of memory on your GPU, then the first thing to do is to lower your batch size. And there's some intricate trade-offs that happen with batch size. Larger batch sizes provide better estimates of the gradient, while smaller batch sizes can provide more regularization. If you're curious, check out my class. There's some more details on kind of how to choose a batch size. In practice, though, it's really, I don't see it having a huge impact. It can, but there's other things that usually matter more first. And then finally, normalize. So what this does is it takes our data, and it can be helpful for these deep learning models to have the images pixel values be normalized between 0 and 1, for example, or to some predetermined mean and standard deviation. So here we're using what's called ImageNet. So ImageNet is a big open source computer vision data set. And we're going to be using a pre-trained model shortly. In ImageNet stats, that represents the mean and standard deviation of ImageNet. So by normalizing by ImageNet stats, we're taking our little brickball cylinder data set, and we are making it look a little bit more like the data that the model was trained on, where we're just scaling it, basically. So it's pretty simple, but it can help. So we're doing that as well. So I'll go ahead and run this, and we'll get a nice error. Oh, yeah, this is called path. Okay. I should go ahead and change this because I want my notebook that I'm making from scratch, I want it to be identical or as close as possible to the one that I provided you, just in case you're kind of blending code from the two. So I'm going to change the name DataPath to just path so it matches better. Path is a little bit general, but that's okay. All right. Cool. Okay, so this should work. And we should get a new image data bunch, and you'll be surprised to learn how close we are to actually training a model. Okay, cool. The next thing that FastAI has built in, which I love, are some easy visualization methods. So if I go to data.show batch, I can visualize a batch. And let's see, I think I get to pick the number of rows and columns that I visualize. And let's have a look here. This should give me a row by column, 5 by 5 view of the data. Let's see if oh, there we go. Look at that. That's pretty. Ooh, this is kind of zoomed out there. That's weird. Okay. I'm going to make this size a little smaller. I believe I can pass in something like fig size, maybe. Is that right? Let's see. Let's see if that works for us. It's just a little bigger than I wanted. Let's see if that. I think it uses matplotlib and it passes in keyword args. Let's see. Oh yeah, it's a little smaller. Okay, I can live with that. All right, cool. So here's our data set, and it's always a good idea to visualize your data set. A million things can go wrong when you stage data, so it's helpful to look and say, is that actually a brick, right? Is that a brick? Is that a cylinder? Is that a ball? So hopefully these labels are mostly correct. And let's see if we can find an example of data augmentation. You may actually already be seeing them. Here's a great example. So look at this data, right? So this is Nature magazine, right? And notice that it's backwards, right? How did this happen? The original image is not backwards. It looks like that, right? But this is our data augmentation. So our data augmentation that we applied by using Git transforms has flipped this data for us, which is pretty cool. Now you want to be careful because not all data is equally flippable, right? So if you are training like a text recognition algorithm or something like that, or something where, ooh, another good one is autonomous driving. If you're training a car that you want to drive on the right side of the road, you should probably not flip your training set because then the left side of the road will be the right side of the road, right? So do pay attention. Here, it's true that balls, bricks, and cylinders are invariant under flipping, right? A flipped ball is still a ball, right? So it's okay to flip. But in general, be careful. You won't always want to flip your data. Okay, so that's our data. And now we're really getting close to learning. I think what we can actually do, we're going to make something called a learner. So I think, is it load learner or is it just learner? I don't think it's load learner. Let's see. Is it like that? No, I might have to cheat. Let's see here. All right, I'm going to have to cheat. Man, embarrassing. All right, let's see here. CNN learner, that's what it is. All right, cool. So we're going to make this object called a learner in FastAI. And a learner holds a bunch of really good stuff for you. So it's going to hold your model as part of the object, and it's also going to hold your data. Pairing those together is something that out of the box PyTorch and TensorFlow aren't really going to do for you. They can, you can build it, but it's really built into FastAI into the way it works, which makes things a lot more convenient. So I'm going to make this learner object, and here are the things that we need. The first thing that it's asking for is a data bunch, right? And we made one of those. We called it data, right? So I'm going to just pass in data as my first argument because we have this. If we scroll back up here, well, that's fun. Okay, if we scroll back up here, and I'm probably okay. Well, I might try this. Okay, I'll try full screen again just to give you a little better view. Cool. Okay, so we have an image data bunch called data. That's great. So we're going to pass that in. And what is the next thing that we need here? So we need a base architecture. So this is a deep learning architecture, a base architecture. So I believe in FastAI that's stored in a variable called models or a class called models. Yeah, there we go. Cool. So if I get some nice tab completion, which has been hit or miss so far. Oh yeah, thank you, Collab. Good. Okay, great. So these are the models that are available in FastAI. So there's a decent selection. There could be more. Other libraries may have more, but you can get a lot done with this collection of models. So these are the models that are available. One of my favorite models to go to is ResNet. So let me go to ResNet here. And as you can see, there are 5 ResNet options. So there's 101, 152, 18, 34, and 50. The number after the ResNet corresponds to the number of layers. So a model with more layers is deeper. It's a larger, heavier model. It takes longer to train, but it can give you better performance. But it may overfit. So I like to start around ResNet 34. Some folks like ResNet 50. It depends on the size of your data set. If you have a really tiny data set, you may consider ResNet 18. But I would just experiment. It's very cheap and easy to conduct experiments. So we're going to try ResNet 34. If I press Shift-Enter, I kind of want to see what happens. Oh, nothing. That's pretty exciting. What if I do this? Oh, yeah, that's what I want. Cool. Okay, great. So we're going to be passing ResNet into the learner, but I just wanted to show you kind of what's under the hood here. So this is a It's really a PyTorch graph. I think this inherits from a PyTorch module called inin.module, I think. But this describes the architecture of the neural network. If you're new to deep learning, this is going to be like Latin to you, and that's okay. If you've been around for a while, though, you probably recognize some of these things. And again, this is a great thing if you want to look at my course, or there's other courses out there that will explain what some of these things mean. But these are the layers of the neural network. The first layer is called a conv2D. This is a convolutional layer. Really, it's just a piece of mathematics. What you're really doing is you're taking these raw pixels in the image. You're taking a little sliding window that's 7 by 7 pixels. You're moving it over the image. And you're computing what's effectively a dot product, multiplying all the numbers together, adding them up for each position on the image. That's a convolution. And the cool thing about deep learning, is that you're going to learn the optimal set, maybe not optimal, but you're going to learn a set that works well of weights that will be plugged into this kernel that will help this convolutional layer recognize basic patterns. So it's really like learned pattern matching is what's happening. There's a bunch of other stuff going on. You'll see conv2D happen a lot. You'll see a lot of batch norm. Batch norm is a way to normalize your data as it goes through your network to help your model learn more effectively. Really, it's about normalizing the gradients. But this is a relatively new invention. I think the batch norm paper was 2015 or something, but it really helps your models learn. ReLU, this is very important. I'll just talk for a second about it, but I'll try not to go too long here because we have a lot to do. But ReLU is what's called a nonlinear activation function. And neural networks can learn what are called nonlinear patterns, which allow them to effectively do very complex tasks. If you took out all these ReLUs from the model, it would learn terribly because it would be a combination of linear layers, which a bunch of linear layers together makes for a linear function, which could not learn complicated nonlinear patterns. So it's kind of like, it's really interesting. You're injecting a little bit of weirdness kind of into your model, a little bit of nonlinearity. And by doing this, you can learn these more complex patterns. It's really interesting. So again, I don't have time today to get into all the math and stuff, but it's super fascinating. I encourage you to check it out. The best book on the theory by far, if you're interested, let me go out of full screen here. The best book for sure is Goodfellow Deep Learning. So it's all available online. If you do want to buy it, it's like $70. I don't get any money for saying that. I wish I did, but I recommend this book all the time. But here you go. So if you want to learn some of the math, Goodfellow Deep Learning is outstanding. It's a really, really good book. I use it in my course. And it will tell you all about the stuff that I'm talking about, except it'll tell you better because Ian Goodfellow is way smarter than me. All right, cool. So that's ResNet. The last thing I want to look at is the output, maybe. Let's see if that helps us learn anything. Okay. It's actually not very helpful. We'll look at some more stuff like this in a minute. Oh, no, that is helpful, actually. Yeah, that's pretty cool. Okay. I just want to point out one thing, and then we'll move on. Out features equals 1,000. So what this is basically saying is that the input size, input space, input dimension is the size of your image. That's the input. The output dimension is 1,000. If you want a fun trivia question, maybe think to yourself, why is it 1,000? The reason is that this model was pre-trained on the ImageNet dataset, which has 1,000 classes. So class number 78 might be dog, class number 602 might be cat, and this was trained on ImageNet, which has 1,000 classes. So the dimension of the output has to match the number of classes, which we'll see again shortly. Okay, cool. So that is the model we're going to use. I'm going to pop the model into here like that, and I'm going to close this, maybe like that. Yeah, cool. All right, great. Oh, that just moves me up and down. Okay, cool. Now I think I need one more thing, Let's see. So cut, this is kind of cool. You can break apart graphs into smaller graphs. We're not going to do that right now, though. Let's see. Custom head, we're going to do that later. We're going to leave that out. I think we need a loss. No, actually, it's going to pick the loss function for us. Yeah, that's pretty cool. Yeah, all we need is metrics. That's pretty cool. Okay. So we're going to type one more thing, which is metrics equals accuracy. So accuracy, oops, you got to spell it right. Accuracy. No? All right, cool. So accuracy is a easy way to measure performance of these models. There's problems with accuracy, so don't always use accuracy, but it's a good starting point. And if you have a balanced data set, it's a pretty good indicator of performance. All right, cool. So I'm going to make this learner. Here we go. So we're going to make this learner. Okay. Oh, this is cool. So it's downloading the weights from PyTorch. So it gets the weights, and we now have a learner. Cool. Okay, excellent. So let's now get into some training. Yeah, excellent. So I have some notes in here if you want to follow along. I'm going to go back to the notebook I've been working on. The first thing I'm actually going to call is learn.freeze. Learn.freeze. So let's talk about what that does briefly. So, excuse me. So there's a bunch of numbers in this model. So the Resonant 34 is like, I forgot how many parameters. It's tens of millions, something like that. So think on the order of 10 million parameters. So there's a bunch of numbers in here that are supposed to magically map your image to your class, which is the fact that this works is just witchcraft. It's crazy. It's crazy that I'm talking to you about this and it actually works. When you're first training your model, so by default, the learner will pull a pre-trained model. So this model will be trained from the ImageNet dataset, and it's going to be this pre-trained model. You can set pre-trained to false if you want and train from scratch. I generally recommend starting with a pre-trained model unless you just have a huge dataset, or you have some reason not to. But what learn.freeze does, it's very interesting. So I think, let me show you one more thing actually. So if I go to learn.model, let me show you this real quick. Yes, this is exactly what I wanted to show you. Okay. So this is the model that we just looked at, right? We just kind of walked through all these layers, tons of mathematical operations that happen to your data, right? And on the output, this is called the head of the model usually. It's kind of the output here. The thing I want you to pay attention to really, a couple things actually. So here's something cool. Out features equals 3. So why is that 3? Remember it was 1,000 before, right? It's 3 because we have 3 classes. We have brick, ball, cylinder. So FastAI inferred that by knowing our data set, right? So it inferred that from our data set, which is pretty cool. It automatically set up our graph the right way. Now, this part is called the head. And what freeze does is it's going to freeze, or it's going to make all these weights that are pre-trained, it's going to make them not learn except for the head. It's only going to make the head learn. What I can't remember in this moment is I can't remember if it only lets the very last layer learn or if it's the whole head. I can't remember. You'll have to look it up. I wish I could remember, but I'll look it up later. But so it's either going, just the thing to know is that most of the network is frozen. It won't learn, and it'll just train the very end. The reason you would do this, right? So why not let your whole model learn, right? Why just train the end? So one reason is it's faster. Another reason is that if you have a small data set, and our data set is actually pretty big, but you can use deep learning on very small data sets. If you just train the end, you're less likely to overfit. It'll train faster, you can run experiments more quickly, and it's usually a good starting point because sometimes you won't need to train the whole model. And training the whole model may make you overfit. So learn.freeze is usually a good place to start. It freezes the whole model except for the outputs, the last few layers. And it might just be the last layer. I can't remember. Don't quote me on that. But it freezes most of the graph. That's the thing to know. Okay, one more cool FastAI trick to have, and I'm going to go ahead and run the code, and then I'll tell you what it's doing. So the code to run is learn.lr_find, open paren, close paren. And I'm going to go ahead and run this, and then I'll tell you what it does. And you may want to go ahead and run it yourself as well, because it'll take a little bit of time. Do I have a GPU on this? We'll see. We'll see how fast. If it takes like an hour, there's no GPU. We'll see. Okay, so what is happening? So when you train deep learning models, there are what are called hyperparameters that you have to set that are going to kind of set up the rules of training. How's it going to train? How's it going to learn? There's many hyperparameters that go into a model. There's quite a few. And notice I'm saying hyperparameters, not parameters. So the reason I don't say parameters is because, does that say 5 hours or 5 minutes? All right, we'll see. The parameters are actually, those are the weights that your model learns itself, where hyperparameters are the things that we set as algorithm designers. The most important hyperparameter is what's called the learning rate. That's how quickly your model learns. How big of a step does it take as it optimizes its weights? The bigger your learning rate, the faster you will learn, but if it's too big, you won't learn effectively. You may jump over good areas to optimize, basically. So finding the right learning rate is really critical. And while I'm saying that, I'm thinking that, is my runtime actually a GPU? Let's see. Ah, there's the problem. This is great. Okay, so I'm running on a CPU, and I think that's 4 hours. Maybe it's 4 minutes. I'm not sure. It's too long, is what it is. No, I guess it's 3 minutes. It's still way longer than I want to wait, though. So what I'm going to do is I'm going to go to runtime, and I'm going to change runtime. And you've probably already done this because you followed the instructions, unlike me. I'm going to save this. So we're going to have a new runtime. I am going to have to rerun some stuff. I don't think I have to re-download data, though. I shouldn't have to. Let's try to not do that. Unless it actually changes VMs. Colab is doing some secret sneaky stuff on the back end. Oh yeah, it's doing secret sneaky stuff. This is a whole new environment. Interesting. Okay. All right, so I'm going to have to run it from the beginning. That's okay though. Hopefully I can get my data set pretty quickly. And what we'll do here is we'll get that lrfind function running. And what that's going to do is it's going to test various learning rates. Is what it's going to do. It's going to help you find the best learning rate. Again, it is the most important parameter to pick. There are some methods that can automatically pick it, but it's still probably the most important one to pick, and it's still, I would say, in 2020, difficult to automatically pick. So here we go. We have our data set downloading, and as soon as that comes in, we will do this find LR thing. That's going pretty fast. I hope your experience is similar to mine. All right, cool. So we made a learner. We're going to freeze, and we're going to LR find. Excuse me. Okay. So we should get down there in a second. If we don't, I will. Oh yeah, it's doing our visualization. I should have commented that out. That's okay though. So here's another visualization we can just look at while it's thinking. So balls, bricks, cylinders. Cool. Okay, great. So lrfind is running now. Excellent. Okay, so this should be, yeah, look at that. So now it's going to take like 9 seconds per test or something. All right, cool. So while it's running that, let me go and get my plotting code ready. And I think it's going to be learn.recorder.plot, I think. We'll find out in a second. We're going to generate this plot, and it's going to show how our loss function, and we don't have quite enough time today to get into the details of how loss functions work, but just know that it's a piece of math that measures how well you're doing. And the lower it is, the better, and the higher it is, the worse. So the lower the loss function, the better your model's doing. And this plot that I'm about to show you, as soon as this finishes, it's going to show you how does the loss function change as a function of our learning rate. If I change my learning rate, how does my loss function change? So that's what we're going to see in a second. And we're going to use that plot to figure out an optimal learning rate. That's what we're going to do. So let's see here. Yeah, I think it will stop automatically if it begins to spike or something. So it says they're doing 10 tests at different learning rates, I think. Okay, so yeah, it should just be a few more seconds. So hopefully you're running on your end and it's working. I have a sinking feeling that we are dramatically behind time here, which, let's see here. Yeah, I was shooting for bounding box 25 minutes ago. Wow, okay. So let me just say this. So hopefully the pace is good for those at home. If you're really bored and want me to go a lot faster, feel free to chat, and Roberto, maybe you can tell me. I hope this is a good pace. One thing that I miss about doing these in person a little bit is you get a little more feedback in person about if it's the right pace. But if this is too slow, please let me know. I can go a little faster. It's no problem. Or if it's too fast, let me know. So Roberto, if you see any chats I should be aware of, just I can't see the screen right now, unfortunately. But if there's any chats I should be aware of, just let me know and I can adjust accordingly. Okay, so let's see here. We finished. Okay, great. So I'm going to run this. All right, sweet. So there's our plot. Great. Okay. So yeah, so this is the learning rate as a function of, this is the loss function as a function of learning rate. So as I increase my learning rate, how does the loss function change? And what this is doing, just for a little more context, is it's changing the learning rate and it's taking a step downhill in the downhill direction of the gradient to reduce our loss function. So as you can see here, if I have a very small loss function, like let's say 1 times 10 to the minus fifth, like 1 over 100,000, right? And if I take a step downhill and I try to optimize my network, nothing really changed. I don't really learn. My loss does not go down. And the whole goal is to make your loss go down, right? As I get to this part of the curve, I can see that, oh, hey, look at this. If I have a learning rate of like 1 times 10 to the minus 2, 0.01, then if I take a step downhill, I learn a lot, right? I go from a loss of 1.8 down to like 1.2 or something, which is pretty good. Now, this is interesting, right? So if I go too high, hello, hey. Okay, wonderful. Thank you, guys. I appreciate that. Yeah, so we won't get through the whole thing. I apologize, but maybe I'll emphasize we might skip one of the training modules and go to the deployment module. We'll see how we're doing on time. And all the material is there, so you should be able to run all of this yourself. Hopefully, yeah, if you're interested, it's all here. You can run it all. And I put notes in the notebooks as well, so if we don't get to everything, it should still be very accessible. Okay. So here we are, right? So if the learning rate is too high, right? Learning rate's too high, then our loss function is going to spike. peak, basically. And what's happening here, imagine in gradient descent, so you're trying to find like a valley, here's the idea. So if you're really interested in this, actually, let me share one more thing with you. The first YouTube video I ever made was called Neural Networks Demystified, and it's kind of embarrassing, but because now there's just so much better stuff out there, like probably the 3 Blue 1 Brown series is a good one to watch too, but I'll just show you my own real quick. Here we go. So if you're interested in kind of the theory, this video series will walk you through how gradient descent really works. And there's another good one, the 3 Blue 1 Brown neural networks. This one's really good. This one's better than mine. You should watch this one. But mine's maybe a little bit more geared towards Python. Mine's in Python. Yeah, here we go. Cool. So this one's really, really good too. So if you're curious about kind of the theory of gradient descent, check those out. Okay, so back to where I was. So the main thing to know then is that you want to pick a learning rate that's going to make a difference, but not too high of a learning rate. I don't like to go down here. I like to kind of be on this curve. I'll usually pick kind of the middle of the curve, maybe a little bit lower. I'm going to pick 1 times 10 to the minus 2. And this is not an exact science, and that's really the state of machine learning today. It's not an exact science, and that can be a little scary, but it also makes it kind of fun, I think. Cool. All right, so we're going to train this sucker. And let's see here. How do let's just start with learn.fit. Okay, so this is pretty cool. So if I want to train my model, all I do is call learn.fit. And let's see here. The first thing it's asking for is the number of epochs. So an epoch is just a pass through your whole data set. So we're going to say, okay, learner, how many times do you want to pass through this data set? And we'll have it pass through just once to get going, just to see how it goes. And it's also asking for a learning rate. So let's pass in our learning rate. So I'm going to say LR equals LR to pass in our learning rate. And I'm just going to train this. So I'm going to train it for 1 epoch, and let's see what happens. So I'm running this, and let's see what we get here. So it's going through our epoch here. It's training. It's going pretty fast, which is good. Okay, now it's going to measure the validation loss. And let's see. Okay, cool. Excellent. Oh, I don't love that. Okay, it's a little messy. So this is a good thing to talk about, though. So it's trained for 1 epoch. It took 18 seconds. The accuracy is 65, which is okay. It's better than, just for reference, if we had just guessed randomly, our accuracy would have been around 30% because there's 3 classes. It's like flipping a coin with 3 sides somehow. But over here, here's what I'm concerned about. Here's what I don't like. And I think it's going to go away in a second. I think it's fine, but it's worth talking about. So the training loss is 0.88, right? And don't worry about the units here too much. This is a cross-entropy loss function, so it's kind of like there's not really a unit to worry about. But it's like a probability. Well, not quite, but the thing I'm worried about here, though, is that the validation loss is significantly higher than the training loss. What that means to me is we might be overfitting, right? We might be doing well in our training set and kind of memorizing it, and just doing poorly on our validation loss. If you deployed a model like this, there's a chance it's going to do actually way worse than you measured, and it may do way worse than this, right? So I do believe the accuracy is on the validation loss. Actually, I'm sure it is. So this number is not on the training set. So this probably is real world accurate, but overfitting like this is a little bit concerning. Now, I don't think that that's going to persist, and what I want to do is train for 4 more cycles just to see what happens here. I think it's going to kind of move in our favor, but it's something to pay attention to. So let's train for 4 more cycles, and let's see if we can get a little bit better performance. And I'd say another thing about fast AI to pay attention to is it encourages you to change your kind of workflow. So when I first started working in neural networks a long time ago, and even into like 2015, 2016, 2017, I would kind of design an experiment and then let it go run on a server or my desktop or wherever for like a day or something stupid, right? And that's kind of how it went, and that's still true for some. Ooh, that's nice, 93% accuracy, nice. So that's still true for some models, but with fast AI in particular, you can run experiments like this really fast, and you can do it interactively, right? And doing this stuff interactively is a big deal because you can make decisions like this. If you have to wait 12 hours every time you make a design decision, you're just not going to be in a good state of flow. You're not going to perform as well. You're not going to be able to experiment as much. It's not as good of an outcome. So I encourage you to find a way to be able to run fast experiments in ML. And sometimes that means taking a tiny sample of your overall data set, just taking a little baby version, or maybe training on smaller sized images, whatever it is that allows you to do quick iteration. Because quick iteration is you're just going to get where you want to go faster, and having that long delay time between seeing your results. Sometimes you have to put up with it, but if you don't have to, don't. So that's my advice on that, at least. Okay, cool. So here's our results. We made it to 94% accuracy, which is pretty good. I think we can do better. We still appear to be overfitting a little bit, which I'm a little nervous about, but it's not terrible, but we are overfitting a bit. The other thing that I'm sensitive to here is that our validation loss went down, and then it kind of went back up, which again makes me a smidge nervous, but it'll probably all work out, but just things to pay attention to. Going down and coming back up, again, check out my neural network series if you'd like to learn more about that, Neural Networks Demystified. This can happen, again, if you overfit. Basically, you train for too long, your training loss continues to go down, but your validation loss spikes up, basically. That's a sign of possibly overfitting. So let's keep going here. I'm just curious, but here's what I want to do. I want to show you one more thing real quick. So there's this great thing you can do in FastAI. You can save checkpoints, and of course you can do that in other frameworks and libraries, of course, but FastAI makes it really easy. So I'm going to save, actually I'm going to call it classifier 1. So I'm going to save a checkpoint, basically, and I'm going to run another experiment, and if this experiment goes badly, which it might, you never know, I can reload, right, my old checkpoint. Hopefully that makes sense. So like if this experiment goes badly, I'm going to do learn dot, I believe it's load. We can try in a second and see, but if the experiment goes badly, I will load that old checkpoint and kind of start back where I was. So let's see. Oh, that's looking better, yeah. So this data set, it was very hard 50 years ago when this kind of thing was proposed, and it was honestly still probably pretty hard 10 years ago, but we're going to be able to get very, very good performance. I don't think quite 100%, maybe 100%, depends on your train validation split probably, but I think we should be able to do pretty well. We're still overfitting a smidge. Let's see where we end up here. How did this go last time? Let's look. I made it to 96. Cool. Oh, and then I did differential learning rates. Okay, we'll probably do one more trick. That's what we'll do. All right, let's see how we're doing here. 96%, 98% accuracy, that's pretty good. Oh, look at that validation loss. That's exciting, 0.02. That is cool. We might call it quits here. Let's see. So notice we haven't even unfrozen our network, right? Only the last little bit of the network is learning, not the whole thing. So we'll see if we need that. We might not. 97%, that's pretty good. Okay, great. Let me go back to my notebook. I'm kind of curious what's possible. If you're experimenting at home, see how high you can get. Feel free to chat what your accuracy is. Looks like last time I got to around 98%, which is pretty good. I think for now, let's keep moving. Yeah, let's keep moving. So I'm going to go ahead and grab some code here. So in the interest of time, I'm not going to train the whole model. It might get us to like 98 or 99% accuracy, but we're already at 97, which is pretty good, right? So let's go ahead and start looking at some of our results. So what I'm going to do is I'm going to use this FastAI class called classification interpretation. I'm going to load one up from a learner. They love these class methods in FastAI. Cool. All right, and I'm going to load it up like this. Oops, like that. All right, cool. So I'm going to load this interpreter thing. And this is going to help us kind of look at our results and see how we're doing. So I'm going to run that. Okay, pretty exciting. Now, yes, I'm going to plot the configure. So I'm going to do interp.plot confusion matrix. Let me just run that and see what I get. Okay, cool. Let me make this a little bigger. Fig size equals 10 by 10. Cool. There we go. That's too big. All right, let's go a little smaller. Let's go. I drive my students crazy at UNCC doing this kind of stuff because I want it to look like perfect. But all right, 6 by 6. Let's see. All right, that looks a little better. All right, cool. Okay, so this is called a confusion matrix. You may have seen them before. Let's talk through it briefly. So this is a great way to visualize how your model is performing. So the rows of the confusion matrix represent the labels that humans, my TAs and myself, created. And the columns represent the predictions of our deep learning model. So this 2, for example, actually let's talk about the 40 for a second. The 40, these are 40 images where the label is cylinder and the model says cylinder. So these are 40 correct examples. So as you can imagine, if everything was on the diagonal, then we would have perfect performance, right? This would be a perfect model. Not everything is on the diagonal. This is why we're not 100% accurate. So there's 2 examples where the label is actually cylinder and the model says brick. And this can help you see how your model is confused. So another really great function in FastAI, let's say I want to visualize those two, what do they look like? I can do interp dot, let's see here, yeah, plot top losses. Yeah, there we go, that's what I want. Let me show I think this will be a 2x2, or that's going to be a 4x4 grid. No, it's 2x2. Cool. Okay, great. And again, I wish it was a little smaller, so I'm going to make it a little smaller. And let me actually plot. Can I have 9? Let me try to get 9 of them. Okay. And fig size, we're going to do 8x8, maybe. That will be good. Too small. Okay, we're getting close. What this is going to show us is it's going to show us the examples that the model got most wrong. And a lot of times you'll find weird stuff in your data set by doing this. It's very helpful to look at the quality of your labels by looking at the examples your model got most wrong. So this first one, our prediction is ball. So the model says ball, but the label is cylinder, right? And this actually gives you the loss function value and the probability. So it's very wrong, basically. It has a high loss function value. I don't know why I got this one wrong. It doesn't really look like a ball to me, but to the model it does. Same problem here, ball cylinder confusion. And maybe from this angle, you can have that nice rounded edge, right? So maybe it looks like a ball, possibly. And this one, oh, this is actually really, I like this one a lot. This one's kind of fun, right? So this is a cylinder. The model says brick. What in this image might trick our model into thinking a brick is there, right? I think it's clearly this book. This book looks kind of brickish, right? It's got these nice hard edges. So that's interesting, right? Same thing here. We got brick detection again. It's actually a cylinder. And then this one, let's see, the prediction is brick. Oh, and that same thing, yeah. So it thinks this is a brick. And then, oh yeah, this one it actually got right, but it had a high loss function, so it had a low confidence basically. It wasn't super confident about this example, and you can see the ball is pretty like obfuscated right behind this greenery. Cool. Okay, great. Oh, and it got this one right, but it did struggle a little bit. This one's fun, right? So all these books, right, and there's the ball hiding right there, and it still gets it. That's pretty cool. I can tell it got it right because it's ball, right? So, so there you go. Cool. Okay, great. I think there was one more plot I wanted to share, or is that it? Oh, there is one more thing I want to do together, and that's going to be important shortly. So that's the result. So this is a pretty good classifier. It's not perfect. You could probably train it some more. You could try unfreezing. We'll do some of that in the next notebook. But 97% ain't bad, especially for how fast this was. So let's go ahead and save those weights, and we're going to save them in a place that we can actually deploy them later in a web service. So we're going to export the weights locally, and I showed you earlier there's this file system kind of attached, right? So I'm going to put these in a home directory, and I'm going to call this bbc classifier.pkl, pickle. It's a pickle file. And let's see, where does that actually know? It's up, yeah, okay, and that's at home, and then there it is. Cool, okay, great. So we've saved the weights to this virtual machine that's sitting behind this collaboratory thing, and we're going to use these weights later in a web service. So there's actually 2 more steps we have to do. And actually, we didn't have to actually do this. Apologies. This is still a nice thing to do because what you can actually, this is the reason I had you do this. So if you can find it here, you can download it to your local computer if you want to deploy it in a different way than we're going to do it here. So if you don't want to use Google Drive or something, you can download it. So this gives you a way to download this file locally if you would like to by exporting it and saving it to the file system. The other option, if you'd like, is you can save this to your Google Drive, and then your web service can automatically pull the weights from Google Drive, which is pretty cool. So I'm going to mount my Google Drive. This might not work for all of you. And I think this actually, if I run this in front of you all, it's going to show like a private key thing, which I probably shouldn't do that, but let me just run this real quick. Yeah, okay. So what you do is, yeah, I'm just not going to do it. Okay, right, cool. But if you're running this at home, what you can do, since a bunch of people are not watching your screen, is you can click on this link. It will give you a code. You put in the code here, and it will authorize this notebook to mount your Google Drive. So I'm going to stop interrupt execution. Cool, okay. And the last thing to do is after you mount your Google Drive is to save the model weights in your Google Drive. You probably need a path kind of like mine. Like you probably have a My Drive at the top of your Google Drive, I'm guessing. You may have to experiment a little bit with this. I made a DSGO folder in Google Drive to save my weights, and then I save them as a pickle file. So if you run this cell and this cell, you will have a set of weights that came from the model that you trained on this data. And we can later deploy those into a web service. So cool. So that is the first section of our talk today. Let's see how behind schedule we are here. I guess this could be a 5-hour talk. That's pretty crazy. All right, so it's 5:30 in Charlotte, which means it is 2:30. We're an hour and a half in. It's 2:30 on the Pacific Coast. Okay, cool. All right, we may blow through our break then. Hopefully that's okay with everyone. If you need a break, just take one. But we may keep moving here just to get some stuff done. We've got about an hour left, and I want to make sure we get some good stuff covered. So we won't get to deployment quite yet, but I want to make sure that we save time for it, because deployment is super cool. It's just the neatest thing that we can do all this stuff. So that's classification, and hopefully you feel a little bit like you've solved one of the oldest problems in computer vision, which is pretty neat. There's a little bit more to it. Part of their kind of their plan, I think, was to actually localize these shapes. I don't know if they say it here, but they do say it, I believe, elsewhere. Yeah, I think they talk about finding the objects. Anyway, a natural extension of this work is not just to classify and say, hey, an object is present, but to find the location of the object. So let's go ahead and give that a try. And to do that, I'm going to open up our next notebook here. So I'm going to open up our second collaboratory notebook. So here we are. And this is kind of annoying. You'll have to download the dataset again, I believe, because I don't think there's probably a way to do this. I'm sure some folks out there can tell me some really smart way to share your data across multiple probably by mounting the Google Drive or something. There's probably some cool way to do it. For now, I'm just going to re-download. But if you have a slick way of getting the data across multiple Colab notebooks, feel free to do so. And what we're going to be doing in this notebook is we're going to be adding to what we've done so far. We're going to use a similar network, but we are going to predict bounding boxes, right? Which is kind of the next layer of complexity, right? So can we figure out what's in an image, but also, where is it in the image, right? So that's the next layer of complexity here. So I've downloaded my data set here. Hopefully it's working for you as well. I'm going to import my same libraries. I'm also going to import a library called JSON, JavaScript, I think object notation is what that stands for. This is just a library that lets us import our label files. And I'm going to go ahead and start the same way I did last time. So let me insert a couple blank cells here just so I can talk as I go. So let's see here. Oh yeah, and I'm using keyboard shortcuts to insert cells. I'm using Control M and then B. But I think, how do you do this without that? You can do insert, yeah, code cell, cool. There you go. So you can do it like that as well, if you'd like to. And there's probably some other ways to do it, I'm guessing. All right, so here's our data. And same data as last time. And last time we used classification labels in the CSV. And this time we're going to use these bounding box.jsons. So let's go ahead and load that up. So we're going to use, I'm going to get rid of this cell if I can. Now my keyboard shortcuts don't work in Google Colab quite the same way. That's okay. So here are my labels. I'm going to load up this JSON file. And when you load JSON into Python, you generally get a dictionary. And I'll just go ahead and print that whole thing out just so you can kind of see what we're dealing with here. It's going to be a little messy, I'm predicting. Let's have a look. Yeah, nice and messy, right? Okay, cool. So this is the JSON file. And let's kind of try to understand what's going on here a little bit. There's 1,000 labels in here. I kind of regret printing this. That's okay though. At least it didn't crash anything. So if I can keep scrolling for, oh man, oh my goodness gracious. All right. Okay. This print everything strategy is terrible. Can I do this? I think I can. All right, cool. All right, don't do that. I do not recommend printing the entire JSON. That's terrible. All right, I don't know how that was a good idea. I think it's kind of helpful maybe because you get to see all the stuff. Just accept for me that there's a lot of stuff there and that it's a dictionary, I would say, is all I would. Did I run that again, please? Okay, good, I did not. Good. All right, I'm going to delete this terrible cell, and then let's keep going. Okay, so it's a dictionary. I can prove it to you if I do type. If I do type of labels, it should say dict. Let's see. Yeah, it's a dictionary. Cool. These are the keys of the dictionary. So it has 4 keys. It has images, annotations, type, and categories. So let's kind of drill right on in. If we look at the labels or the annotations, field of that dictionary. And let me just give just a smidge more context. I do kind of want to make sure I'm not just flying through a bunch of stuff here. So labels of annotations. This is going to be crazy. Let me do this. Let's be smart. I think this is going to be a list. Let's see the length of it. How many annotations are there? Yeah, there's 1,185. Why is that more than our classification? That's interesting. All right, so let me insert a cell below. So let's look at annotation label number 12 just to see what its structure is. Oh yeah, this is why it's crazy. Okay, got it. So this is made by a tool called LabelMe. And this is the annotation for the 12th image. This is the name of the image. And remember I told you that we have those like dense segmentation masks? Let me show you just a visual really fast so you know what I'm talking about. Why can't I? There we go. Cool. Okay, yes. So you see how we have just certain pixels colored, right? So to have just those pixels colored, oops, sorry about that. Let me hop back to here. Cool, okay, great. So to have just those pixels colored, we have to draw this mask around it basically, and what you're seeing here, these are all of the control points of the region basically. We don't need those. We'll use something like that later, but right now we're going to just use the bounding box corners. So all we need is actually this. So these are the corners of the bounding box around the object. So that's cool, and that's what I pulled out here. So this is the bounding box corners. Okay. So we could write our own JSON importer. That wouldn't be too terrible, I don't think. But we're going to use the FastAI one. So FastAI has a method called Git Annotations, and I think you just give it the file name. And I believe it works with this format like the one we have here. And it's going to give us back two things: a thing called images and a thing called label bounding boxes. And I believe that they're both lists. I believe. Let's just confirm that really fast. So if I do type of LBL bbox, cool. All right, it's a list. Yeah, great. Okay, so if I look at the first 5 elements of images, this is the name of the first 5 images in the dataset. And if I look at the first bounding box, it has zipped together the name of the classification label with the bounding box. And the label was also in the JSON. That's where it got it. And it has the bounding box. Notice that this is a list of lists. I believe that's so it can support multiple bounding boxes per image. So that is what our data looks like. And we can visualize our data set, and we're going to do that using this image bbox.create from FastAI again. And OpenImage is also from FastAI. We pass in the path. So here I'm just indexing through the data set. So I'm looking at the second image and grabbing the second bounding box to go with it. I'm grabbing the coordinates and the class, and then I'm showing it, again using a FastAI method. So later we'll use some matplotlib. But here I'm just using the built-in FastAI methods, and I can kind of click through here and visualize some stuff. There's a great widget called the interactive widget that you could use here to really kind of click through. But it's helpful just to kind of put in some numbers, look around, poke around. Poking around your data set is really, really valuable. So that's what we're looking at. Pretty exciting. Cool. Okay, so that's our data set. Now we need to get our data into a format that FastAI can work with. And last time we used what's called an image data bunch. This time we're going to use a slightly more specialized loader. We're going to use this object item list from FastAI. We're going to do the similar thing to what we did before, but it's going to be in this functional notation, which is kind of weird. But you can actually do this either way, but this is a little bit cleaner in this case. But we're going to make this getData function that, given a batch size and an image size, creates a data bunch that we can use to load our data. We have to make a method that goes from or maps from the image name to the bounding box coordinates. And what Jeremy, I've stolen this pattern from Jeremy Howard, the founder of FastAI. He uses a lambda function here, which is great. It's a nice simple way to do this in Python. And this is called getYfunc, and we pass this into this label from function method, and this takes care of basically the object item list passes in a name of an image, and getYfunc loads that, and that gets loaded into our data loader. Just to show you really fast, like this is not it probably looks a little crazy, but it's really not too bad, I promise. So image to bounding box is just a dictionary. Let's load real quick. So printing a bunch of stuff in Colab is a little messier than, oh, maybe it's fine. Maybe I'm just complaining. No, this is definitely messier. Let's see here. Ugh, terrible. I regret this immediately. All right, so how can I make this shorter? It's a dictionary. I can't just do this, right? There's no way. Yeah, it doesn't work. Okay, that's fine. So this is a dictionary. I guess I could do this. So for k comma v, I'm just trying to give you a sense for this data. K comma v in mg2 bbox dot items colon. No, that's not going to work either. How do I get just the first thing? All right, this is going to be really hacky. Do not judge my real-time code. This is pretty embarrassing. All right. Oh, that's not even going to work either. Oh god, that's terrible. I was going to do a quick break. There's some really easy way to print the first 5 things. All right, I'm going to try one more thing, and if I can't get it, then we're just going to continue. Let's do this. I just want to show you what this dictionary is. Oh, I have an idea. Okay, I have a hacky idea. All right, here we go. Just to show you what's going on inside of here. Here's my hacky idea. We're just going to take the first 5 things. The other thing you don't have in Google Colab is you don't have multiple cursors, which is mildly annoying. Okay, so now I can print this because it's just the first 5 things. There we go. Okay, cool. So this is a dictionary, and the keys of the dictionary are the names of the images, and the values of the dictionary are the bounding box coordinates. And all Lambda does is it takes an O, which is a full path to an image, and it gets O.name, which is just the name of the image in that path, and it just samples this. So it's just a really simple function that you hand it an image name, and it gives you a bounding box coordinate. So I know that code can look a little bit overwhelming at first, but it's really not too crazy. It does something pretty simple. Okay. So now I'm getting some transforms. We talked about these last times a little bit. So this is doing transformation. I have max rotate equals 0. I don't remember why I'm doing that. It may not be required, but this turns off rotation basically. So I'll leave it on for now, but I'm thinking it's not required. So this is interesting. So TFMY. So this is really interesting, I think. So remember that we're passing in all these transformations. So get transforms, right? Even with max rotate equals 0, it's still going to do a bunch of stuff, right? So let's look at what we get. Yeah, so it's going to do flip left to right, symmetric warp, it's going to zoom, it's going to change the brightness, it's going to do some cropping and stuff. So it does a bunch of random jiggling and perturbations to our image. And what's the problem with that, with bounding boxes, right? The bounding box has to move with your image, right? So if you're not doing that, your labels are going to be wrong. So again, something you can certainly code yourself, or there's other libraries that can do it, but in FastAI they make it super easy. You just say transform y equals true, and it will transform the y, the bounding box coordinates, as well. Excuse me. Okay, so that's how we're going to get our data. I'll keep moving for now here, and we're going to use, oh, that's fun. Oh, I know what happened. So my little trick here of just using the first 5 gave us not all the data, right? So that's not good. And I think our image folder had more images in it. So we need to go back to having the whole list of images. And I bet our problem is fixed. Fingers crossed. Yes, excellent. Okay, cool. So we're going to do an image size of 256 by 256 pixels and a batch size of 64. Here is our data set. So the X value is images. The Y value are the image box objects, which is a FastAI box representation. Let's go ahead and show a little sample of our data set. And we should see some augmentation, and we should see some data. Let's see if we see any augmentation. I don't see anything obviously like squished or flipped or anything. Let me run it again. If you run this again, it does another random sample. I'm just curious. I just want to make sure that our augmentation is doing what we think it is. It should be doing like random flips and scales and stuff. This brick looks a little stubby. I think it is being squished, I think. Although I want to believe that, so I could have some bias. I would like to see a flip, like some words backwards. That would make me very confident. Let's see. Oh yeah, I love it. Nature is backwards. Good. So flipping is working. And I'm just curious, if I turn on rotation, does this break everything or no? Like, can we rotate bounding boxes in FastAI? I haven't done that in a while. Let's see if it's possible. I don't remember. So I set rotation to 10. Oh yeah, yes, here's what happens. So the rotation doesn't get adjusted after rotating or something. I think you could fix this, but right now, if you're doing bounding boxes in FastAI, see how big this box is, right? I think that's because rotation is not, I don't think the bounding box coordinates are getting rotated properly. That, or I can't remember if it's not a solvable problem or if it just is not implemented. I'm not sure, but for now, we're going to turn rotation off. So that's the reason for that, is it might make our boxes artificially large. Okay, cool. Alrighty, that ball is really hiding there. Okay, so let's get into the modeling. So here's our modeling section. We've got our we've got our data loading pipeline. And let's see here. So, oh yeah, this is going to get really interesting, right? Okay, let me make sure I spend a little bit of time really talking through this because this is important. So last time we used this learn. Well, we used. Have I set up a learner yet? I have not, right? Yeah. Okay. Cool. Yeah. Last time we used this models.resnet34, right? Okay. Cool. And here was where I think things get interesting. I'm not just going to like pull up some magic bounding box model. FastAI does not have implementations of bounding box models like YOLO and stuff. It might get added eventually, but it doesn't have those things, and that's okay. That's not really what it's designed for. It's really designed for quick experimentation. You could certainly implement Fast or YOLO in FastAI, but what we're going to do here instead is we're actually just going to make the minimum modification required to our last model to be able to just solve this task. And for a moment here, I'd like you to just forget about classifying for a second, forget about brickball cylinder, and just think about the bounding box for a second, right? So remember last time we had to have the output dimension of our model be equal to 3 because we had 3 classes, right? 1 output unit for each class. Now here, think about how many things do we have to predict, right? How many things are we predicting? And if you think about it carefully, right, to predict a bounding box, we need like an upper left corner and like a bottom right corner, right? So we need 2 corners. So that's parameterized as 4 numbers, so like an xy and an xy. So this is going to sound hacky, but it's really how things kind of work. What we're going to do is we're going to create a custom part of our neural network, and we're just going to make it have an output dimension of 4. So that custom part is called a custom head. So here it is here. And there's some stuff going on here, and I'll talk about it briefly, but the thing I really want you to see is this 4. So the reason that this is 4 is because I need to predict 4 things. The x1, y1, and the x2, y2, the 2 corners, right? So the custom head is nothing too special. So this adaptive concat pull2d, don't worry about this too much. What this does is it takes a variable sized output from what's called the backbone of the model, and it shrinks it down to 4x4, basically is what it does. The next thing is flatten. So this takes a convolutional volume of data and it rolls it out basically into a one-dimensional vector of data. Dropout is a way to reduce overfitting. If you find yourself overfitting a bunch, try to increase the number. And I think it's increased. Let's see if I can confirm that. Let's see, nn.dropout. Let's see what the docstring says. Okay. All right. So P, yes. So P is the probability of an element being 0. So the way dropout works is it randomly turns off parts of your model to actually make it learn a little less effectively, which helps reduce overfitting. So the probability of making an element 0. So yeah, actually, so if you want to increase your dropout and make your model overfit less and make it learn less, basically, and overfit less, you actually make this closer to 0. So I had that backwards. So I'm glad I checked. Cool. So these are what are called linear layers. They're matrix multiplies that are learned, basically. This is a little bit hairy. Where the hell did I get this number 16384 from when I made this custom head? So let's talk about it for a second. Where did I get that? So I got it from, let me go back. I know I'm going to use resnet34. Let's look at the very output of resnet. Let's see if I can explain where this came from. Okay. So this is the head of the default resnet, and I'm going to replace this part with a custom head. This batch norm 512, what this means is that I have a data volume that is 512, it's 512 units deep, or 512 pixels deep is how you can really think about it. And what I'm doing here, oh yeah, this is tricky, there's a lot going on. Wow, okay, I forgot about this too. Anyway, we have this volume that's 512 pixels deep, and then it's 4 pixels wide and 4 pixels tall. So kind of think about it as a 4x4 pixel image, but it's very, very deep. That's kind of how our data gets shaped as it goes through the network. So how many values are in that? Well, it's 4 times 4 times 512. That's how many unique values there are that move through the network. How many? It's really a bunch of math on top of the image gets transformed into this data block. That gets us to 8192. Now I'm multiplying by 2 here because this adaptive concat pull2d I believe this actually does. Is that what it is, or is it the adaptive average pool TV? Don't quote me on that right away, but I believe what's happening here, and you can experiment with these numbers if you have to. Like I'll show you what happens if it breaks in a second. But I believe we're taking the what's called a max pool and an average pool at the same time and concatenating them together. So you end up with this times 2 factor, basically. I believe that's what's happening. But let me just show you. Let's assume that I got this wrong and just show you how it breaks. I think it's fairly fixable, but this could happen to you. So let me show you. So let's say I took 8192, which I know is the wrong number, and I put it in here, and I made that my custom head. The output is right, but I'm not like mating it or matching it to the backbone correctly. So before I load my learner, and I think this is going to error because I put in the wrong number. Watch it just work. That'd be funny. So this is my loss function. And I have to create a custom loss function here. So that's another bit of complexity. So last time, we just let FastAI figure out the loss function for us. Now we're going to have to be a little bit more picky. So this takes a little bit of trial and error, and you can look at the docs and the source code to figure this out, or you can borrow my code. But what this does here is I'm inheriting this from inin.module, which is a PyTorch parent class. And I'm overriding the forward method. And the method is going to get an output, which is the output of the network. It's going to get something called bounding box targets and class targets. The reason the loss function will get that is because of the way I set up my data loader. So my data loader has both coordinates and it has labels. That's what this image bbox thing contains. So in my loss function, which measures my performance, I take in bounding box targets and class labels. And I'm actually going to ignore the class targets for now. I mentioned that, hey, forget about brick, ball, cylinder. Let's just worry about finding the bounding box first. Then we'll do the other part later. So I'm going to take those bounding box targets, and I'm going to do what's called an L1 loss. An L1 loss is just taking the difference of two values and taking the absolute value. That's all we're doing. And I'm doing it for all 4 of those points. I have to do this unsqueeze thing. This is a way to like pad a dimension in PyTorch. So if I have like a 2x2 matrix, if I unsqueeze it, I can make it like 2x2x1, for example, which is needed here because it needs to match the dimension of my bounding box targets. So I do this unsqueeze thing again. Again, this is mostly stuff you can do by trial and error. I'm going to try to show you some trial and error in a second here because this should break and we'll see how to fix it. I think it's going to be pretty straightforward, but we'll see. So I have my own loss function now, which measures how different 2 bounding boxes are. And I'm going to create a CNN learner. And now I'm passing in this custom head, and I'm passing in my own loss function. So another nice thing in FastAI is you can see a summary, and this will show you kind of what happens to your data as it moves through your network. And it actually hasn't complained yet. Oh, maybe it's going to complain now. Let's see. Oh, yeah, there we go. Okay, so let me show you. So size mismatch. So you have matrix 1 is 1 by 16384, and matrix 2 is only 8192, right? So this is a hint. It's a hint of what's going wrong. And of course, the problem is what I described earlier, right? This should actually be the dimension that we get out of ResNet. And you can do trial and error for these things if you don't want to do the math. I'm going to put that right there. And now, fingers crossed, our error should go away. So yeah, there we go. No error. Cool. So this is pretty cool. This is a nice way to look at, this is just learn.summary. This is a nice way to look at the architecture. So remember that our input size of our images is 256 by 256. And as our images pass through our network, they're getting smaller and we're doing more and more mathematical operations to them. There's a few notebooks in my class that kind of visualize these steps. We don't have time for that today, but it can be cool to kind of visualize what's happening, although it's not might not be as illuminating as you might hope. There's a lot of mystery in how these things actually work. So for each layer, this is telling you the number of parameters that will learn from data, and this is telling you the dimension of your data as it goes through your network. So we have all these layers. It's getting smaller and smaller and smaller. It goes down to 32 by 32. It gets deeper, smaller and deeper. 256 should get even smaller and deeper. Yeah, smaller and deeper. All these parameters. This layer has 2 million parameters. Wow, it's a lot of parameters. And here, so this is what I wanted to look at just briefly together. This is what's happening. So this is the output of the backbone, and this backbone is getting flattened and like made into a vector. And that vector is what feeds the head of our network. We do dropout, a linear unit, batch norm, and then this is our output, and our output dimension is 4, just like we wanted. So our model has 25 million parameters, pretty exciting. That's interesting. Trainable parameters is 4. I thought that'd be higher for some reason. Maybe it's because it's frozen. Let's try an experiment. That should be higher unless I'm just forgetting something silly. Let's see. Is the model frozen? Let's see. So if I do here, do learn.unfreeze, just to see. I'm just curious to see if the trainable parameters changes. Let's see what happens. Ah, look at that. Okay, cool. So if I unfreeze, all the parameters are trainable, right? And actually, we can actually resolve a question I had earlier, which was when you're frozen, and you can freeze various stages. If you just type freeze, though, I think it just freezes the head, I think. I would bet $10. Let's see if I'm right. So if I type learn.freeze, and I think in here you can pass in some arguments to just freeze, I think, separate parts. So anyway, let's have a look here. So I do want it to be frozen right now. I don't want to train the whole graph. And let's see here, trainable parameters 4213. So yes, so it's this plus this plus this, I think is 4213. So yeah, so it's the whole head, basically. It's not just that last linear layer. Okay. It's not just that last linear layer. It's this whole section that's getting trained. Okay, cool. All right. And yeah, time is flying, man. Okay, great. Oh yeah, because we have Q&A, that's right. Shoot, okay, cool. So let me close this out real quick. And yeah, we can actually deploy pretty quickly. So I'll pause there for now. What we basically do here in object detection is we train our model, we use LR-find. It's very, very similar, actually super similar. We train, we visualize results. And actually, let's see if I have them. I don't have them visualized here, but that's okay. So yeah, I'd recommend looking through this. Let me go ahead and spend a little bit of time talking through deployment, because I do want to make sure we spend a little bit of time on that. And we did save that model earlier. So if you continue that notebook, you will see, let me go back here, you'll see how to train a bounding box detector. And then there's one more notebook on segmentation. So it is almost, yeah, we've got about 10 or 15 minutes. So let me go ahead and hop down to deployment real quick, because I know that's an interesting area that I think a lot of folks have expressed interest in, and I think it's an important area. So we're going to use a service called Render, and we're going to deploy that classification model that we trained, the first model that we trained. So you will have to create a render. You will have to create a render account. It is free. So I'll go to render.com here. I'm going to sign in. I think I signed in with GitHub. Yep, cool. So here I am signed in with GitHub. So yeah, if you're following along, please go ahead and go to render.com and just make an account. If you want to sign up with GitHub, that's a super easy way to do it. Everything we're going to do here is free. You won't have to put in a credit card, I don't believe. And let's walk through how you actually get this thing deployed. So the first step, really, as you're setting up your render account, so do that first. And then on the GitHub website, you want to create a fork of this repository. So the reason you have to do that, so you go up here and you go to, where do we fork here? I almost never fork repositories. There it is. You fork up here. Cool. That will make your own copy of this repo. And the reason you need to do that is because you're going to point render at this GitHub link, and it's going to go to that link, and it's going to use that code. Now, what I would like you to do, you don't have to do this, but what I'd like you to do is you can fork the repository, and you can change the location that render will look for, or that render will look for your model weight, so it'll actually pull your model weights. If you run this, it'll pull my model weights. I'm not sure, you shouldn't get a permission error though. It should actually work because I made my model weights public. But let me show you what we're getting into here. So the first thing, create a render account. The second thing, fork this repository. And now let's kind of get into it here. And I have step-by-step instructions you can follow at the bottom of the repo in section 7. And what we'll do here is we're going to deploy this brickball cylinder classifier. So as I said, you'll need to point, there's a little bit of web server code in here, and I'll show it to you in a second. You'll need to point it at the right file. So you're going to modify this app/server.py. So let me kind of show you where that is real quick. There's two options, really. You can clone the repo to your local machine if you want, like we talked about at the beginning, or you can actually edit it right in GitHub. So let me show you the GitHub option. It's maybe a little easier. So if I go to app and I go to server, this is the web server that we'll use to serve up our application. And it's actually pretty straightforward. I encourage you to check it out at some point. It uses the Python async library. And this is from FastAI. I modified two things, maybe just the download file. Yeah, but this really is from FastAI. There's a good lecture on this. I think it's lecture 1 in their deep learning course. But so I borrowed this web server from FastAI, and it's a really nice little application where you can deploy these models. And the thing to change here is way up here, this export file URL. And you can change this again. You can clone the repo and open it up in a text editor like this, and you can push the change if you're comfortable doing that. Or you can just modify it in GitHub by clicking Edit. And if you click Edit, you can actually modify it right here, and you can commit a change. So let me go back here real quick, and let me show you where this link comes from, right? So in the first notebook, hopefully you did this learn.export thing, and yeah, right here, right? So you exported this, and I think I have mine pulled up right here. Here it is. So here's where I exported this file to in my Google Drive, and I believe I have instructions in the README, so check those out. But I believe what you need to do is you need to share that file on Google Drive and get a shareable link. So let me show you real quick. Again, the instructions are down here. Yeah, so okay, cool. Okay, and then once you've done that, yeah, create a shareable link from the file in the Google Drive. Cool. So yeah, these are the instructions, and there's a little bit of nuance to it. Let me show you real quick. It's not quite as straightforward as you might like. So I go to share. I think I go to share. Let's see here. Cool. Get link, copy link. Cool. Anyone with a link can, yeah. And you think you're going to have to change your permissions here. So I have some notes on that to make sure. So look at the instructions. You have to change your permissions, and you get the shareable link. Now, like I said, there's a little bit of nuance here. Let me show you that real quick. So let me go back to my app. Let me go to server.py. Let me go to edit. So I'm gonna copy in that link, or paste in that link that I just copied. So here is the link. Now here's the kind of tricky part. This link does not just work. It might work for you. It didn't work for me. I had to do a little bit of finagling here. So this number, this is the ID. So it's in between d/ and then it's before view, basically, if you look at the URL. So copy this. You want to copy this, and you want to replace the part of my string, right? The ID equals, so everything after here, and this instruction is in the README. You want to replace that with this string. So this is the unique identifier for your file, right? That's like the key. So that's the change you'll make, and you'll commit it to your repo, and that will have your web server. It will actually pool your own weights, which is pretty cool, right? It'll dynamically pool when it makes the server. It'll pool the weights from Google Drive, which is pretty neat. So that's how you change, or that's how you point the server where you want it to go. And let me show you one more thing. The way this really works, and kind of the magic of all this, is Docker. And actually, before I chat about the Docker file, let's go ahead and get the render server going, and then we can chat about Docker all day. Let me go back here. So here I'm in render, and I have 2 of these already kind of going. I've done 2 tests, but let's do another one. So I'm going to go to new. You shouldn't have any of these yet. I think you'll go to new. You'll create a new web service. Oh, man. Okay, cool. So I have hit my free trial limit. That's how live demos go, right? Let me see here. If I delete this one, can I create a new one without having everyone watch me put in my credit card number? Let's see here. If you're able to do that, go ahead and create a new one, and you'll do from GitHub, and the instructions are here. So if you don't have to just follow exactly what I'm doing. The instructions are here, and you will. Let's see, what will you do? So. Oh yeah, you can run this locally if you want. Yeah, that's fine. Okay, cool. Deploy and render. Cool. Set up a render account. No credit card required, apparently, until you get to your third service. So create a new web service and point it to your forked repository on GitHub. And that's really like the main thing you have to do. You'll watch the logs. You can try this right now. While you try that, I'm going to try to do it myself, but I'm going to have to delete maybe this one. Let's see if that, yeah, delete web service. Cool. Now let's see if I'm able to create a new one now. Cool. So I'm going to go to new web service. Come on, no credit card. Good. Okay. So this is linked to my GitHub. You may have to put in your GitHub user here, possibly. There might be a little bit different interface for you, but you should be able to hopefully link to your forked version. So I've clicked on my main master version, but you'll have a fork of this. So let's call this BBC classifier. Cool, classifier, oops, v3. Okay, environment is Docker, and I'm going to pull from my master branch. Cool. All right, create web service. All right, so that should be all you really have to do, and this is just the coolest thing ever. So it's going to clone the repo automatically to a server, and it's going to use the Docker file to build a Docker image and then a Docker container. It'll run a Docker container. Excuse me. So, and you can do that locally too if you'd like to, but it's pretty cool that Render does all this for you. So let me look, let me show you. Oh yeah, here we go. Excuse me. So this is the Docker file that actually runs the web server. So this script, there you go, it's already running. That's so cool. So this is pulling in, let's see, I guess a Debian Linux version. And it is, what are we doing here? Cool. Let me go to the bottom. All right, cool. So it's setting up the environment and everything. I think in this Docker file, we must be telling it, yeah, it's using this slim stretch container to start from. Cool. All right. And it's installing some dependencies we need, Python 3, GCC, and it's installing the requirements list. These are a very similar list of requirements to what I showed you at the beginning. It's pip install. It's copying this file, pip installing it, copying all the app data, and it's going to ultimately run this app, basically, right? It exposes this port 5000. That's the port that the traffic goes over. But this actually is all you need to set up a Docker container that serves this model, which is just the coolest thing. All right, so let's see here. Building. So it's still building. We got a race against the clock here. This is dramatic. So we'll see if our web service finishes building before Q&A time. I guess if it finishes during Q&A, we can still show it. And I do have a backup, but I kind of, okay, cool. I do have a backup we can show, but I kind of like the drama. We'll see if we beat the Q&A time. So it's installing these packages now. That's cool. There's Jupyter, you can see, NB format. Prometheus, wow, I don't know where that got in there. That's interesting. All right, cool. So it's installing all these packages we need. That's pretty cool. Okay, oh, it's doing that copy step now. So it's copying all those app files over. It's running the server. Oh, I think we're almost there. Oops. Let's see here. I think we're almost there. Exporting image format. All right, cool. We're getting close. When it's done, it should say that the server is running on port 5000, basically. And then we should be able to actually run this thing. Let's see. Or access this thing from. And actually, once I have this up, you guys can actually hit it as well. So let's see here, exporting to OCI image format. Let's see. All right, I think we're getting close. Let's see if there's anything else I want to share about this. We didn't have time for GANs today. You can also run this locally if you'd like to. It's pretty straightforward if you clone it locally, if you want to play with it. And you can also, of course, serve this from Azure, or from AWS, or from Google Compute Engine. But Render really has just a super easy, it's just a few clicks, which is pretty nice. So I think we'll be up and running in a second here. And if we aren't, I'll go to the backup. But I do kind of want the live one to work. I think that'd be pretty cool. And I think it's about to, it should look like this, actually, when it's done. Cool. All right. Drama. All right, cool. And we didn't quite get all the way through object detection. Again, I encourage you to look at that notebook if you're interested. It's all there. Hopefully that's helpful. And again, the Fast AI lectures are very, very good. I'm sure I put some links in the notebooks to those lectures. They also will walk through all this stuff. Oh, we made some progress. Let's see. Exporting cache. Cool. All right. We got a little warning about PyTorch. Yeah, like a versioning of PyTorch. Hopefully that's okay. All right. Okay, and I think maybe get your browsers ready. Pushing image to registry, cool. So get your browser ready, so you can try this as well. Or if you have your own running, that's great too. So the link here is going to be HTTPS, and let me, can I put this here like really big? Yeah, cool, okay. So this is the link. I'll make this really big. You should be able to go there, and you can try the web service that I just literally instantiated. It's not quite done yet, but if you go here, bbc-classifier-v3, and you're in HTTPS, on render.com, if you go there, you should be able to hit my web server that I just set up. Although it's not quite done, it's close. Let's see here. All right, since we're about to hit Q&A, I may switch to the backup, but during Q&A, this should become live, and you should be able to actually run it. Let's see. With that, that's the Shocky or something. Okay. Let me do this. So I do think it's very close. Let me go to services. So we have, oh, this one's suspended actually. Oh, I can't even, yeah, my backup is not running. Okay, all right, well, we're just gonna wait for the, well, let's wait for the real one. No big deal. Okay, cool. All right, I do think it's gonna be done very soon. Let's see. First, oh, I think it says ready to go. Let's see logs. Come on. Let's try to go to that site. BBC classifier-v3.onrender.com. Fingers crossed. Live demo. Come on, render. This says ready to go. It says started, though. I don't know if that means it's not sure. All right, this is where our web service should pop up, hopefully in a second. All right, well, if we do want to do some Q&A, I'm not sure. I think it's just a couple minutes left. We can keep monitoring this. We should be up and running. And what I might do, just real quick, is I'll start a second one, just in case. I can go ahead and resume this other one. It's the same exact thing. So we'll have two options. I do want you guys to be able to see the real live thing, because it's so cool. Let's see. All right, so deploy started on that one. What I really want to see is v3. Yeah, cool. Okay. The other one is going to be a very similar name when it does become available. I'll kind of get it ready. And actually, I'll just copy it. Well, I'll go here. V1. Cool. All right. So we should, hopefully in a minute, have a web server to actually try out. And it will actually should correctly detect balls, bricks, and cylinders. Of all the technical problems that could happen today, this is not too bad. I was expecting worse. Training deep learning models live is just so many things can go wrong. All right, let's see. I don't know why it's not showing me any logs. Let me open up one more thing, because here's my new one, and it says it's deployed. Nope. Oh, we're so close. I hope we get it by the time we're done. Okay, well, all we can do is let that run. Cool. I can run it locally. Yeah, that's an option. All right, so I think we're about to hit Q&A, which is great, and I'll let this keep loading. But hopefully that was informative. You know, we talked about a bunch of different deep learning techniques. Hopefully that was a good foray into fast AI. As usual, we didn't have quite as much time as I would have liked to get into some stuff. This is kind of the same story in my class. There's just so much to cover. But hopefully that was helpful. We learned about fast AI and image classification. And I think you'll be pleasantly surprised how similar bounding box detection and segmentation are, especially segmentation. It's very similar to classification, very similar steps. You're doing LR find, you're training your model. There's a lot that's going to be really, really similar. So just keep that in mind, and I really do recommend fast AI as a way to quickly try experiments. I don't think it's right for everyone, and especially in production, but it is just a nice library to make experiments go fast, which is pretty cool. All right. All right, I might get my backup going during Q&A if I can. We'll see. Does this one? Oh, I shut this one down. Yeah. Here's what it will look like once we get it to load, and if your version works. It'll pop up at this website. You can load an image, and you can analyze it, and it'll tell you the result. So that's what should pop up in a second. Hopefully it does, but I did shut down this one, or I had to without entering a credit card number. So I think we've got about, let's see here. Is it Q&A time, Roberto?
Yes, we are in Q&A time.
Okay, great. Well, yeah, while this is loading, let's go ahead and if there are any questions, happy to answer them as we're hoping that render comes through here.
All right, well, awesome. Thank you so much for that great workshop, Stephen. I read through the chat. Everyone was super stuck on the presentation, reading, just attentively listening to every word and following every step. They were super involved, and that was awesome.
Great.
I'd like to welcome you now to your very own DSGO live Q&A. The way it works is that attendees will send questions through the chat. I'll receive them and then I'll ask them to you. So attendees, you know what to do. Send your questions to the chat. We have a first question coming in from Anishinder Antal. What is the rule of thumb for deep learning algorithms when creating training, validation, and test sets from the data? Does the ratio differ based on the size of the data?
Yeah, great question. So there's no hard and fast way to do this. I'd say that maybe a common split to do would be like a 70-20-10 maybe, or 70% training, 20% validation, 10% test. But there's no hard and fast rule you have to follow. If you have a really small data set, you may be tempted to use a smaller validation set. I'd probably be comfortable going down to 10%, but it makes me a little bit nervous. But the main important thing is that you do it. Make sure you split up your data set. And I've seen splits like 60-40. That's not uncommon. It really depends on the size of your data set, and it's something to play around with. But I think 20% is a reasonable starting point. But yeah, there's no, like much of machine learning, there's no hard and fast rules.
All right, great. We have another question coming in from Julian Weindel. How do you tackle strongly imbalanced data sets?
Yeah, that's a great question. Ooh, I think we have a server going. Cool. This should pop up in a second, I think. All right, yeah, so unbalanced data sets. Fantastic question. So there's a number of things you can do. The simplest thing you can do is do a sampling of your majority class. So if you have 10 times as many examples of one class, you can just sample a tenth of those or a fifth of those or something. You can do a subclass or a subset, basically. That works pretty well, but of course you are leaving out part of your data, which kind of sucks. Another thing you can do is you can pad the class that has less examples, right? So you can just duplicate examples that you have less of, which is also kind of annoying, but it works reasonably well. Those are kind of the two most common things, and they're really simple, but they do work. And then there are other more sophisticated things. There's some things in the literature you can do. You can change your actual loss function to work a little bit differently. You can take different samples of the class that you have too much of during training. You could try unsupervised learning to just learn on the good examples first. For example, if you really had just almost no examples of the minority class. But those are some of the simpler things that you can try.
Okay, wonderful. Thank you so much. We also have a question coming in from Byron Killian. In production, do you load your model behind a REST API from the model checkpoint object that got persisted to file during training?
Yes. So actually, that's exactly what's happening. Is my screen still visible? Am I able to point to something?
In a second.
All right. Cool. Because I can show you exactly where. It's a great question. All right. Let me know if that's coming through. So this actually is the REST API. So this server is still fighting me, unfortunately, but I believe it will come to life sooner or later here. But when it does, this is actually the REST API. So you define two routes. We're using this library. I think they're using Starlet. Yeah, Starlet, exactly. Cool. So there's two methods, an analyze endpoint and there's a homepage endpoint. And when you call the analyze endpoint, it actually calls learn.predict. So this is actually your deep learning model sitting behind your REST API right here in app/serve in the repo.
Okay, wonderful.
Yeah.
Now, we have a question from Akshat Gupta. If we have very few images to train CNN, like 350 images, then how could we get a high accuracy? Like how many convolution layers or hyperparameters should we use?
Yeah, so this is kind of a big, I'd say maybe a misconception sometimes in deep learning that you need a huge data set. You really don't, and thanks to pre-trained models. So I've had success with the same exact workflow I just showed you, ResNet34, for example, on data sets of like 100, for example. So you actually really don't need huge data sets. It's just all about regularizing. So what Jeremy Howard recommends is you try to overfit first, and then regularize by increasing your dropout, by increasing your data augmentation, by doing techniques like that. And 350 is not unreasonable to use a ResNet34, for example. I know that sounds crazy, only 100 examples and you have 20 million parameters, but it really does work. It's kind of one of the crazy things about deep learning. And just real quick, I noticed my web service is working now, I think. Let's try it. Let's just try it out real quick just for fun. So I'm going to select an image, and this is bbc-classifier-v1 on render.com. So you should be able to hit it too if you'd like to. And if I pass in a brick, here it is. Let's click Analyze and let's see. Hopefully it actually works. There we go. So there we go. So 50 years later, we can do what Seymour Papert and Minsky set out to do, which is pretty cool. So let's hop back to Q&A. But I just wanted to share real quick that we do have it working. It just took a little bit longer than expected.
Well, that is wonderful. I'm glad. I'm super psyched that it was finally working again. We have a question coming in from Ken Langston. In the case of using CE for defect detection in manufacturing, which involves high frame rates and high res, have you worked much on the hardware part of CV during application development, cameras or frame grabbers? Any tips on mastering this area of CV?
Wow, great question. So that's very much my day job. You feel free to email me or reach out if you'd like to talk more. So yeah, there's a bunch of problems in manufacturing. Big images is definitely a problem, as you mentioned. We've dealt with up to about a megapixel or 100 megapixel images, which is definitely a challenge. A lot of the frame grabbers now have pretty good SDKs. So there's some pretty good Python SDKs for GenaCam, for example. So hasn't been too big of a problem for us, but the high frame rates can be a challenge. We generally deploy on pretty high-end GPUs, Tesla T4s, so we can go pretty fast and do a lot of our stuff on the GPU. But yeah, there's a whole bunch of challenges. I think we could talk about that for an hour. Feel free to shoot me an email if you'd like. We can discuss further, because that is what I do day to day, and my day job is try to solve those problems in manufacturing.
Okay, wonderful. We now have a question from Pavan Shetty. Which are some of the untapped domains where CV can be utilized? Any use cases?
Yeah, there's like a million of them. Yeah, so in the class I teach at the University of North Carolina at Charlotte, we have a big course project, and my challenge to students really is to go do something new with computer vision, right? Something that hasn't been done before, or at least is not widely publicized, right? And there's so many cool applications. You can actually, I can show you real quick if my screen share is still working. My course is at github.com/UNCCV, and there's actually a link to it in the README if you're interested. But my course project is here, and you can actually see some of the stuff that students have worked on way at the bottom here. And there's links to their projects, but there's all kinds of cool stuff. And I'll just mention two things that you may not have thought of when you're thinking about what to do with computer vision. So one of my students last year, she implemented a bullying detector. Basically, that's the wrong link. Oh shoot, I have to ask my TA about that. So her project basically was detecting bullying in schools. So she made this classifier to take a security camera feed and detect if there was like punching or kicking happening, like bullying kind of activities, and send an alert basically. So like that's kind of a cool application I wouldn't have thought of. Another group took images of RNA, so actually images that were generated by a program that shows the folding pattern basically, and they used that image to train an RNA classifier to identify like anomalous RNA molecules. So again, not a traditional application, but really cool, right? And then let's see, oh, this is one more I'll just share briefly. So UI wireframe prototype, this was a group of my students last year. Some of these folks are looking for jobs too if you guys are hiring. There's some really great students in my course. But yeah, I guess they don't have I wish they had a screenshot here. What this group did, it's really, really cool. They made a GAN, a generative adversarial network, that you could, if you were like a designer, so what you could do is you could mock up a website, and it would take that mock up and render out like what the final website would look like. It was really, really cool. It wasn't perfect, but it worked really well for some examples, and they could just draw like little boxes that would be like the areas of the website, and then the neural network would predict what the final website would look like, and it could be like a tool you'd use in design basically. It was super cool. So yeah, there's a ton of it's crazy. There's so much cool stuff you can do with neural nets that no one has even thought about yet, I think.
Wow, that is in fact quite a wide range of applications, both microscopic and macroscopic. That's
totally right. Yeah.
We have another question coming in from Miguel Fernandez. Stephen, do you think one can improve computer vision models by including integral channel features plus deep learning?
What was the first part? What kind of feature?
Integral channel features.
Integral channel features, as in like a mathematical integral, maybe INTEGRAL?
Well, it's specifically integral channel features.
Okay, cool. I wish I knew what an integral channel feature is. Maybe that's a paper I haven't read. That sounds really interesting. I'm not sure. I don't know what an integral channel feature is, but if that means like integrating over the channels, like taking the sum over the channels, probably that seems interesting. A CNN basically does that, I guess, by doing a dot product across the depth of the image. But if that's something in particular, I'd be curious to learn more about it. But yeah, I'm not sure.
Okay. Again, Miguel, if you have a clarification, you can feel free to send it through the chat, and we'll ask it. I will add the clarification. We have another question coming in, this time from Sophia. She asks, as a Swift developer, I'd be interested to hear your point of view regarding the future of Swift in machine learning and deep learning. Yeah,
great question, man. So yeah, you got to check out FastAI 2, which I believe is going to be, I think, in Swift, or at least partially in Swift. So yeah, I think this is the next wave. So I'm not much of a polyglot. I really mostly just know Python. I wish I knew more languages, but if I was going to learn one more, I think it'd be Swift, because Jeremy Howard and Chris Latner, who's the author of a number of compilers and stuff, they are working on Swift implementations of a number of these models that are going to appear to be dramatically faster than Python without losing much expressiveness, or maybe even more expressive. Python kind of has this middle layer that kind of gets clunky when you want to go really fast. And I think Swift is probably the most promising new language in machine learning. There's a chance it might all fizzle, you never know, but if I was going to bet on one language for the next 5 years, then Swift I think is a really great choice. And yeah, fast AI too, and the stuff that Chris Latner is doing in TensorFlow for Swift are definitely worth checking out. And I'm curious to see where it goes, and I wish I had time to learn Swift right now.
All right, wonderful. Thank you so much. Now we have a question from Bandita Rao. The question is, what do you do when the CNN is not learning the right features?
Interesting. So it's an interesting question. So it's you may not know if it's learning the right features. You can visualize the layers of your network, but you're not going to really know as a human if it's learning the right thing. The only way you really know is your performance is going to be bad, right, in general. And if your performance is bad, there's a number of things that can cause it. And one of the challenges of deep learning and machine learning is that it's not like other types of programming. So like general, when you're programming something, you kind of have incremental progress. And deep learning just doesn't work until it does, right? And it could just be one little thing. You could have all your code right, but you forgot to normalize your data, right? And that might make it not learn the right features, or just not learn. You might have your labels mixed up or something. You could have a problem with your data loader. There could be so many different problems. So part of the art and science of doing this is just the experience to know where to look to try to debug your models. But don't feel alone if your model's not learning. In my career, I've probably trained, I don't know, thousands of deep learning models. I bet 70% of them never learned anything. It just takes a lot of iteration, right? So just keep trying, and it could be a million different things that make it not learn. Just do the best debug effort you can. This is a whole long topic. Check out the Fast AI lectures. He does some good debugging stuff. And there's no one hard fast rule, unfortunately, about where to look if it's not learning.
Okay, wow, wonderful. Now, a question coming in from Shujiang Tan. It starts by saying it's really interested in the optional part about reflection on studying and working in AI in 2020. Could you please briefly talk about it?
Well, I only have 2 minutes, but I did leave you a deck. So if you want to check out my deck, feel free. It's pretty simple. It is right here. It's Reflection on Studying and Working in ML PDF. And it's just some slides with some quotes from some people that I respect and enjoy, and some people who have interesting perspectives. So feel free to check it out. It is there, and I think just reading this, it will give you 90% of what would have happened if I had presented it.
All right. Now, a question from Kushagra. What would be your approach on building a vehicle plate detection system? Like, which algorithms would work best?
Okay, vehicle is in detecting vehicles, I think probably is what the question is for, I think. So for detecting
for vehicle plates.
Oh, for license plates. Oh, sorry. I'm glad I clarified. Okay, cool. Yeah, that's a great question. So there's a number of different ways you can try to solve this. I think kind of one of the most common approaches is to solve it in 2 steps. So OCR, or optical character recognition, is kind of an area where there are some deep learning techniques, but it's kind of one of those areas where kind of the off-the-shelf algorithms work pretty well, and you may not want to use deep learning necessarily. So what's pretty common is to train a detector that just detects the license plate bounding box location first. So it's like a 2-step pipeline. So step 1, find the bounding box just by creating a generic license plate detector, and then extract that bounding box from your image and then run an optical character recognition algorithm. So it's like a 2-step pipeline. I believe that's pretty much the state of the art. There may be some papers that can do better with just one neural network all the way through, but as far as I've heard, kind of the most common way to do problems like that is in a 2-step pipeline, detection followed by OCR.
Okay, wonderful. Now, a question coming in from Ilka. Have you looked at the Julia language too? And if so, what do you think of it in comparison to Python and Swift in terms of expressiveness and performance?
Yeah, I've coded just a smidge in Julia. I think the goals of Julia are outstanding. I love I think as a programmer, especially if you're dealing with scientific programming, the mismatch between the way code looks and the way math looks is a real problem, right? So you got an equation over here, you got some code over here, and like mapping between the two is like like half of people's graduate school time or something ridiculous like that. So Julia, I think, makes important strides in that area by making the code look kind of more like math. And I'm really oversimplifying it. There's a lot more detail to Julia that I just don't know, but that's kind of my understanding of it. And that's just an outstanding goal. I think right now Swift has more momentum than Julia, probably, but you just don't know. Julia has a lot of great ideas in it, and it could be a huge language soon. I think I'd probably bet on Swift right now just because of who's involved, and these things are they just kind of come and go. But I think Julia has a lot of cool stuff going for it. I haven't seen a lot of deep learning in Julia, but again, I might just be unaware of it. But a lot of nice design principles in Julia, and I think at the end of the day, for me as a practitioner, just Python has so many libraries and stuff that I just kind of live in Python mostly. But I'm very interested in other languages, and I think Julia does some really interesting things.
Okay, wonderful. I think we have time for one more question.
Oh, okay.
Bhaskar Krishnamurthy asks, any idea on how to use transfer learning in facial recognition?
Good question. So I'm guessing you're asking it in the context of facial recognition because you're maybe assuming that transfer learning from ImageNet model, like the one we just trained, may not work for facial recognition. So I'll say two things. I'll try to keep it brief. So thing one is that we just used I didn't call it transfer learning, but we just used transfer learning to train both those models because we started with a pre-trained model on ImageNet. Doing that is a huge step forward than training a neural network from nothing. Even if you're recognizing faces are close enough to what you see in ImageNet that pre-training on ImageNet is going to help. Really, pre-training on ImageNet helps with everything I've ever seen in my career. The second thing is that you may want to you could get more specific and try to train on like a data set like the Celeb A data set, for example. Celeb A, I think it has the name of the celebrities. You could classify a celebrity based on their image. And that may do better. I would like to see a paper that compares pre-training on ImageNet versus pre-training on the Celeb A data set. Unclear which one would be better. Celeb A does have images of faces, so it may do better. So you could try pre-training on a more domain-specific data set like that. But it's an open question. I wouldn't be surprised if it didn't matter too much which one you pre-trained on. Celeb A may help, but I'd be curious to see some results there. But there's two ways you could do transfer learning for face detection or recognition.
Well, awesome. Thank you so much. I think that's all the time we have for the Q&A, and I think we can all agree this was a very interesting Q&A session. Thank you once again, Stephen, for that awesome workshop and that great Q&A. Thank you for joining us. It was a pleasure hosting you, and again, the audience was thrilled to have you.
Great. Yeah, thanks so much for having me.